Namaskar, a very good morning to you all. I welcome you to the one-day online workshop on aerosols, measurement, retrieval, and impacts today. This one-day workshop is intended to give an overview of the measurement techniques, retrieval approaches, and scientific insights related to aerosols, highlighting the recent advances and emerging research opportunities. We would be covering the following topics. First session will be on aerosol physics, optics and impacts by Dr. Yogesh Kant, Head Atmospheric Science Department, IIRS. This will be followed by a talk on aerosol chemistry by Professor Neeraj Rastogi from Geosciences Division at Physical Research Laboratory. The afternoon session will begin with remote sensing of aerosols by myself, followed by a session on modeling of aerosols by Dr. Narendra Ojha from Space and Atmospheric Science Division at PRL. Finally, we will have a hands-on training by Mr. Akhilesh Kumar from University of New South Wales, Sydney. All talks will be of 40 minutes duration, followed by an interactive question answer session for 10 minutes from the audience. I hope that this day long session would be able to inculcate interest and enrich you with the understanding of multiple aspects of aerosol research. With these words, I once again welcome you all to join this workshop with us. Please be connected. Shortly, we will begin with the first session. So, welcome back. We have with us our first speaker of the first session, Dr. Yogesh Kant, and it is my pleasure to introduce him to you. He is the head of Atmospheric Science Department at IIRS. His expertise spans across thermal remote sensing, land surfaces processes, urban thermal environment, aerosol characterization, and research. He has been contributing to atmospheric sciences at IIRS since 2000. Dr. Yogesh Kant is also a member of several professional scientific bodies, and he has received several national and international recognition for his work in remote sensing and aerosol research. Sir, over to you.
Okay, thank you, Dr. Manu, and the online workshop on the aerosols and properties. And today's lecture will be on the aerosol physics, optics, and impacts. So, wherein we will have an overlook of the aerosol properties and impacts, and what is the health impacts, in fact, and on the environment. So, as you all know, that the atmosphere is composed of different gases, and the atmosphere is the dominantly nitrogen, oxygen gases, and 1% is the trace gases. And the tiny particles, what we call as aerosols, constitute only 0.1% of the constituents. And the aerosols, they are the tiny solid or liquid particles which are suspended in the atmosphere or in the air. And they are very importantly to understand, because they have an important role in the physiochemical, dynamical, and the radiative process of the Earth atmosphere system. And the size ranges, as you see, the size ranges from 0.01 to 100 micrometer. And for example, the solid particles, aerosol particles, are your dust and the fumes. And the liquid particles are the mist and fog. And the solid or liquid particles are your smoke and the smog. And the droplets are larger in size. And we also nomenclature them as the sizes. For example, particulate matter 0.1, it means that the particle sizes are less than 0.1 micrometer. And the fine particles PM 2.5, that is less than 2.5 microns. And all the particles whose sizes are less than 10 are known as the coarse particles. And there are these are also that is the sources. The sources of the aerosols are the natural as well as the anthropogenic. The natural sources are oceans, because largest 75% is oceans. The sea salt, ocean, then deserts, dust, volcanoes, the sulfate aerosols, and natural burning process, the carbonous aerosols. And these are the natural sources, and they almost contribute around 85 to 87%. And the 11 to 13% is your the anthropogenic sources, like particularly the fossil fuel burning, biomass burning, industrial and other waste burning, etc. And also they are also classified like a primary sources, because the primary what are primary sources is that these particles are directly emitted from the source in the atmosphere. And the secondary sources are that the particles, when they are present in the atmosphere, they get reactions, the chemical reactions, and then they are reproduced in the another gas to particle conversion. Now, these next, okay. And now the aerosols, depending on the applications, are termed as differently in the environmental sector, in the air quality, industry, in the atmosphere science. And for example, the particulate portion, which I said, of the aerosol is referred to as particular matter. And this particular matter is also known as particle pollution. And we, as I said, it is classified or categorized as according to the sizes. For example, PM10, PM2.5, PM1. And these are also terminologies are also when the we call as indoor air quality, inhalable dust, like total suspended particles, that is the sizes are less than 40 micrometer. PM 2.5 also we can say as respirable dust, and thoracic PM to 10, like this we also call them. And as I said, particulate matter is a very complex mixture of the aerosol particles or airborne particles. Uh, it can be, for example, the aerosol or the particulate matter does not necessarily exist as a single particle or a single component, because the seed can be anything. It can be nitrate, it can be sulfate, it can be carbonous, anything. But it can be a single particle, homogeneous particle, or a mixture of these particles. For example, it can have a seed core shell of one particle, one component, and on the other there will be another that is shell on it, which is composed of other particle. So it is a complex mixture of the different particles. Now, this, as I said, the PM10, PM10, how it is graphic or pictorially, how it is depicted is that when you compare with the, for example, human hair, that is a particulate matter or size is around 70 to 100 micrometer, we can see that the PM 2.5 is around 30 to 45, 30 to 40 times less or smaller size than the human hair, or 50 times less than the sand. And PM10 is also around 7 to 10 times smaller than the human hair. So that's the fineness, that is small size which we can't see and which exist in the atmosphere. Now, as you see that these are the famous the problems which are concerning in day-to-day life with the aerosols present in the atmosphere, that is the pollution present as a tiny particles in the atmosphere, particularly the visibility in different parts of the world. When you see at different atmospheric conditions, be it India or US or any other part of the world. And also if you see the satellite data, when there is a cleaner atmosphere, we can see all the land and other features clearly. But during the winter time or the other, when the boundary condition is boundary layer is very low, then there is a fog and mist conditions where we miss many of the important visible portions over the earth features. Now the question arises that now why do we care about atmospheric aerosol? Why we have to learn or study about all these kinds of particles? Because first thing is that these tiny particles or the aerosols are creating problem for the human health, and they are the cause for many diseases, chronic diseases, and which have a mortality or deaths, human head deaths due to these particles. Second thing, as I said, when they are emitted in the atmosphere, they also undergo the chemistry, the reactions, and they form the secondary aerosols or secondary particles, and then it changes the atmospheric chemistry. As I said, the visibility, because in the winters and many parts of the world, the visibility causes problem, and it is a financial and transportation sector. There is a financial loss, and also these visibility, the particles are present close to the Earth's surface, and this causes a problem for the human health. Also, these aerosols act as a cloud condensation nuclei and the formation of the clouds. And clouds can have a rain bearing or not rain bearing. They can pose high albedo, and then it perturbs or changes the Earth radiation budget, Earth other radiation balance. Also, these aerosols present in the atmosphere, when they dissolve in the water, that is ocean, and their acidic nature gets transformed in the ocean, and this changes the pH value, and then it becomes an acidic in nature. And many of the aquatic species, they are adversely affected by increasing the acidic nature, and this poses a threat to them. And then there is a change in the ocean fertilization. Of course, finally, all these particles which has a scattering and absorption in nature, they can modify the incoming solar radiation, and then these have an net cooling or net warming effect in the Earth's radiation system, and this changes the climate forcing effects. Now, when we discuss now about the aerosol size distribution. So on the left hand side, we can see that the life cycle and the evolution of the atmospheric aerosols. Now, the precursors, the like for example, the H2SO4 or ammonia or any other organics which are emitted as a precursor gases, and then they undergo the gas to particle conversion process, and then these are in the ultra fine mode, that is 0.01 micrometer, and then they grow in size due to the condensation and coagulation and becomes a fine mode or an accumulation mode, and these are in the range of 0.1 to 1 micrometer. And then these act as a cloud condensation nuclei, that is a seed will be aerosol, and on it water vapor is deposited, and it forms an uh, cloud condensation nuclei and clouds. And these within the clouds, the aerosols are now removed by scavenging and modifying the evaporation process. Now, the larger particle, that is a coarser, or sometimes we called as a giant particles, that is whose sizes are greater than 1 micrometer, they are directly emitted from the Earth's surface by the mechanical process, such as the dust, sea spray, or the volcanoes, or the pollen grains, etc. And they get into the atmosphere, and due to the gravity, because they are larger in size, due to gravity, they have a dry deposition, they come back to the surface or to the wet deposition by the rainfall. Now the lifetime, now we see that in the second lifetime of these are different, because in the aerosols which are in the troposphere, they have a very less lifetime, within a day or within a few weeks. But when these aerosols get into the higher layer of the atmosphere, for example in the higher tropospheric or in the stratospheric layer, so they cause a problem because they stay there for a long time and years together, and they interact with the electromagnetic radiation coming from the sun, and they pose the environmental concern. Uh, Also, the physical size, that is the size of the particles and the shape of the particles, is based on the formation process from where they are creating or they are forming, while the production source determines the chemical composition of these particles. Now, if we see the difference of the aerosols, so in the urban type of aerosol, where in the cities, where there is a different environment, so the aerosols are emitted particularly from the fossil fuel, the biofuels, or the biomass burning, and they are converted to the gas to particle conversion. And the differentiation is that these particles are very fine in nature, the urban aerosols, and the if you see the number of aerosols in the atmosphere in the finer range, that is less than 1 micrometer, are high in number than the coarser or the larger size of the particles. Now, in the second figure, you see this is the urban aerosol, that is the fine, that is the size fine particles, that is whose sizes are less than 1 micrometer, are high in number than the coarser. But if you see the marine aerosol or maritime aerosols, the particles which are in larger sizes, that is larger particles, are more in number than the fine particles. So that's the basic difference, because dust or sea sea salt, they are natural aerosols, and their sizes, particle sizes, are larger than the fine particles. But urban aerosols, they are particularly more dominated in the finer size of the particles. Now, when we talk about the background or the natural aerosols, as I said, the sources, for example, the sea salt, that is the sea spray aerosol. Then dust, we say, that is the second dominant aerosol component, mainly from the desert or the semi-arid regions. Of course, the sulfate aerosols, that are also natural aerosols that are emitted from the volcanoes, particularly because that ends going into higher layer of the atmosphere. As I said, it goes beyond the tropospheric height in the stratosphere and stays for a long time. And then, for example, here, one just example, like there was a volcano in 1991, June 1991, in the Philippines, known as the Pinatabo, and it had infected or impacted a larger region, because the aerosols went in the stratosphere and stayed for a long time, and it impacted not only the Earth radiation budget, but also the temperature, tropospheric temperature as well as the stratospheric temperature. So, the problem is that it injects large amount of the gas, which composed of the particularly the sulfuric SO2 gas, sulfur dioxide, which is converted to gas to particle conversion. That is, it becomes sulfate, and then around 50 megatons it has impacted around in that is injected in the atmosphere, and it went straight to the stratosphere. And the study says that the stratospheric aerosol optical depth, that is the influence of or the impact of the aerosol, has increased, that the pollution has increased by around zero point 0.1. So 0.01 to point or 0.1. And also this has impacted, because when it goes in the stratosphere, there is a photochemical reactions, and then because in stratosphere there is an ozone, and it destroys the ozone. So then there is a depletion, there was a depletion in the ozone, and also it has impacted to increase the temperature of the stratosphere by around 0.1 degree to 0.1 to 0.2 degrees centigrade. And recently there was a volcano from Ethiopia, and in the November last month, and it has also injected approximately 0.2 megatons of sulfur dioxide in the atmosphere, and these not only impacts the troposphere, but also when it goes in the upper layer, it impacts for longer duration. Now, the another question arises, that why when we say that particular matter 2.5 or particular matter 10, so why the size matters? So why this size is important to study, and what is a concern? Now, I have divided like toxicity. That is, for example, if you see the figure, in this figure, we say that this is NOPL. Now, when this is a human respiratory tract, so this is a naso-oro pharyngo-laryngo region, that is NOPL, we say, from that is nose to the throat, and then the tracho-bronchital region, that is TB, short knee, that is from the throat to the lung diaphragm. And these two regions, if you see, because when we inhale, so all the particles goes from nostrils to your throat, and then to the lungs, and then finally goes to the tissues and to the bloodstreams. Through the bloodstreams, it goes to the whole of body and different vital organs. Now, if you see that x-axis has a the sizes of the particles, and y-axis deposition efficiency. Now, in a nutshell, that the finer particles, when we inhale finer particles, the deposition efficiency, be it a throat region or a lung region, is almost 80 to 100% as compared to your larger particles. So larger particle, the efficiency is around 60 to 80%, but the finer particles is more than 80%, sometimes 100%. What it means? It means the particle size is less than 2.5, that is fine particles, when we inhale, when they're present in the atmosphere in larger quantity, and when we inhale, so these particles get inside our lungs, diaphragm and tissues, and then they are dissolved in the blood streams and go to the whole of body. And as I said, the particulate matter is a complex mixture. So the core or the shell can be of different materials. For example, it can be of carbonous, it can be silica, it can be nitrate, it can be sulfate, it can be complex mixture, and depending on that, the poisonous material goes inside the body and it creates a problem for our vital organs. Now, when we discuss about the interaction of the particles with the electromagnetic radiation, that is the light scattering, so we can see that in the visible range around the 550 nanometer, it has a very high efficiency of interacting, and it is very efficient in interacting with the electromagnetic radiation. So it scatters, it absorbs, and it changes the earth radiation balance. So it is very important to study the optics of it. Now, when we also the similar thing, that when we see the settling velocity, that is what is the efficiency of the settling of these particles from large particles to fine particles, we can see that the fine particles has around 1000 to 10,000 times more efficient to settle than the larger particles. And of course, due to the, as you know, the surface reaction, because the fine particles, more is the surface and more will be the area for interaction with the light and other things. So the smaller particles have a greater surface area and the interaction will be more. Now, as I said, these are the same thing which I repeated in the last slide, that when we inhalable particles, that is the total particles I discuss here, that is around 40 or 50 micrometer particles, and then when inhale, and then thoracic particles which are in the range of that is 10 micrometer, and then when it goes inside the lungs, diaphragm, that is PM 2.5, it respirable particles, and it becomes a problem. Of course, as I said, the natural aerosols, they are traveling from one region. The sources are from one region, but it travels to thousands of kilometers and settle and create a problem to other region as well. For example, the North Africa region, Sahara region, there is a vast amount of dust flowing from the west, is thousands of kilometers to the South Asia and Southeast Asia, and in fact there are other regions as well which are the sources, but the impact as around the whole of world in other continents as well. Now, when we say the anthropogenic, because different regions have the predominantly the activities are different. For example, in the Europe, most of the industries or transportation is in the diesel and gasoline sectors. So the particles are of different nature. That is the particulate matter. The seed, that is the core or the shell, is of different nature as compared to the Africa, where the predominantly the biomass burning is the source because of the fuel wood, or due to the anthropogenic activity, the biomass burning, that is the incomplete combustion or the complete combustion, creates carbonous type of aerosols. So that are dominant there. In the northern Africa, there is a dust that is a different material, different cores, and in the South Asia and the Southeast Asia also there are different activities going up, predominantly different activities. So the nature of the aerosols or the chemical composition of aerosol, be it of similar size, the chemical composition will be of different. Now, when we talk about the properties of aerosol, we classify broadly like physical, optical, chemical, and radiative. So we discuss physical, that is the size, the shape, and all that, and as I said, size, that is PM10, PM2.5, or we can say as ultra fine, fine, or large particles, and one more property of the physical is importantly is the refractive index. Now, why we should understand the refractive index? Because this refractive index will tell or give an idea of the type the nature of the aerosol, that is whether the aerosol will have a dominant of scattering nature or the absorbing in nature. For example, this is the real this is mathematically denoted by n plus ik, where the real number is your scattering and imaginary number is your absorption. For example, if you see water, NaCl, that is sea salt, because sea salt, that is sulfate aerosol, though these are naturally released aerosol, and these are predominantly scattering in nature, larger number scattering in nature. But if you see the black carbon or soot, sometimes we say, these are mostly emitted from the anthropogenic activities. You see that the imagery, that is this number, is also high. It means the predominantly it is absorbing, but it will have a small nature of the absorbing, of the scattering in nature, but also it is an absorbing in nature. So this will help to understand the nature of the particle. So for your information, you know what about the scattering and absorption. I need not explain it again. Scattering will conserve the total amount of energy, but the direction will change. But on the contrary, absorption, that is, it will remove the energy and it will re-emit direction and re-emit in another energy form. And there will be a word of extension, that is the attenuation, which composed of the together, that is scattering and absorption together, is known as extension. Now coming to the optical property, that is optical means the interaction of the particle with the electromagnetic radiation. Now this is optical depth, there is aerosol optical depth, that is it is the, what is the extension, that is what is the amount of the scattering and absorption by different sizes of particles at different altitudes. How much is that cumulative effect? What is that effect? That is how much attenuation is given by different particles at different altitude range, is telling about the optical depth. Now what it means, it, in other words, it is also said that it is the amount of radiation that is scattered, that or sent back in the atmosphere before it reaches the earth's surface. For example, if I say AOD is equal to, AOD is 0.2, okay, if it is 0.2, it means it is a clean type of atmosphere, that is the less or very few atmospheric or few aerosol particles are present, so that is less amount of scattering and absorption happens, so it is fairly clean. When I say AOD is 0.6, so it means a fairly good amount of aerosol particles are present. So it is the electromagnetic radiation is being scattered and absorbed, and it means more extension is happening. It means it is a polluted kind of thing. And if I say it is 1.2, it means very heavy polluted event is happening, and very severe pollution is happening over that area. For example, this is in the South Asia and Southeast Asia. If you see bigger region, aerosol optical depth, here you see that the darker colors are mentioning that the more aerosol particles are present, more extension, it means more pollution. So if you see the North India, Indo-Gangetic Plain, if you see the north or eastern part of China, if you see the southeast countries, many regions, there are some high spots of pollution, or the more of high concentration of aerosols. And if you associate with this some of the activities, for example, there is a particular period of time, there is a fire, there is biomass burning, maybe forest fire, or maybe anthropogenic fires, and maybe there may be some industrial activities going on, so that also we can distinguish. And on the contrary, there can be some natural sources. For example, there is a dust event. For example, here the northern Tibet area, there is a dust storm which is natural, but if you see the fire activity, there is no fire activity, but this can be associated, like this high pollution is due to the natural event, that may be dust, if you see the now the absorbing, now you differentiate from the absorbing nature. Now here the absorbing or the black carbon which is absorbing in nature will tell you on the only on the anthropogenic part, that anthropogenic. Here we don't see the dust storms or the natural storms. So like that we can understand using the different properties of the aerosol how different mechanisms or different events are happening and what is the source for it. So this is also in detail of that same figure. Now, now the the another optical property, that is the scattering phase function. Now this the aerosol scattering phase function describes the angular distribution of the scattered light. That is how much light is scattered and in which direction it is. Now why do we know, why do we want to reveal it? Because this will help to reveal about the particle size, the shape, whether it is a spherical or non-spherical, and also the absorption nature of absorption or the scattering nature, that is refractive index. Another that is the property, optical property, is the single scattering albedo. You very well know about the albedo. Albedo, albedo is the how much light is scattered as compared to your total incident light. So the it gives the how much light is scattered as compared to this extinction. As I said, extinction is how much amount is total received, that is scattering and absorption. So if the single scattering albedo is close to 1, it means it is more of scattering in nature, and if the value is around 0 or less value, it means it is absorption in nature. For example, I have listed here, that is if suppose is dust, as you know there is a natural aerosol, so the single scattering albedo is around 1, so it means this is the scattering in nature, as compared to your black carbon which is less value, that is close to 0, and lower value, so it means it has a absorbing in nature. So that also we can estimate through different optical properties, one property or a combination of one or more properties. For example, here this is typical the different seasons, winter, pre-monsoon, monsoon and post-monsoon, and these are some of the parameters. Aerosol optical depth, as I discussed. So if you see the winter season, because of the fog and other things and the other anthropogenic activity and the different due to meteorological conditions and the geography, the more of the aerosols are trapped in this region, and we see the high dense of the pollution, that is more of the number of aerosol particles as compared to your pre-monsoon and monsoon region. When we see the single scattering albedo, that is, as I said, single scattering albedo gives the absorbing or scattering in nature. So if you see here, that is in the pre-monsoon time or the monsoon time, when there is a dust, larger particles, so it will be more of scattering as compared to your post-monsoon and winter time. And we can also estimate here absorbing type of AOD. In this AOD, there are total aerosol particles, that is scattering particles as well as absorbing particles. But if you want to eliminate only or highlight only the absorbing aerosol, that also can be done. Now another property, optical property, is asymmetric parameter. Now this is when the electromagnetic radiation interacts with the like for example air molecules, which are very spherical in shape and very small particle. So the scattering is uniformly distributed, that is within all angles. But when the particles grow in size, that is aerosols larger in particles, so the scattering is not uniformly distributed, but it is as maybe it will be in the, sometimes it will be more in the forward direction or sometimes it will be more in the backward direction. So as a thumbnail, if the particle sizes increases, that is 2.5 or pm or 10 micrometer or more than that, so more of the scattering will be in the forward direction, the scattering in the forward direction. So if you see, like for example dust, sea salt, so more of the scattering is attributed in the forward direction. and if you see the smaller particles, they are uniformly distributed. Also LiDAR, because when we see when we want to have a information over different vertically over different layers, different heights above the earth surface, so we use LiDAR information to diagnose what are the type of the aerosol particles, what is the at what height the particles are situated, and from moving from one place to another place. So in the that is trajectory, when air mass trajectory, that is the dispersion of the pollution, we also require the different layer height. It is traveling from one place, when it is traveling from one place to another place. Now coming to the aerosol, as I said, aerosol are the cloud condensation nuclei. They are the seed. They start the cloud condensation nuclei, and this cloud condensation nuclei forms the clouds. Now the aerosol have a direct effect, that is there is the scattering. Natural aerosols have a scattering of the electromagnetic radiations, scattering nature, and the anthropogenic has a absorption nature, more or less. So then there is a scattering, there is a cooling effect, because most of the electromagnetic radiation is sent back to the space, and less amount of energies reaches on the earth surface. And in the part of the absorption, it is redirected towards the earth's surface, so it becomes a warming. Now these aerosols also have an effect on the cloud properties. How? Because there is known as indirect effect, that is the aerosol modify the cloud microphysical properties of the clouds. And when there less amount of aerosols are present in the cloud or in the atmosphere, so the cloud condensation nuclei are less, they are larger in number, and this will help to form the positive impact on the precipitation, that is rainfall. But when there is more pollution, these clouds have a smaller droplets, the size becomes smaller droplets, and they have a higher albedo, that is they are bright in color, that is they reflect more of the sunlight back to the space, and this becomes less efficient for rainfall, and this forms a cooling effect, because most of the light is scattered back to the space. Now also in the semi-direct effect, what happens is when absorbing aerosols are present here in the cloud, so they burn off the cloud, and they change the c- uh, cloud microphysical properties, and this creates a warming effect. So depending on the particle nature, the size, shape, and the chemical properties, they have a different effect on the clouds. Of course, in the aerosol biogeochemical cycle, because these aerosols are emitted in the atmosphere, and then, as I said, they are dissolved in the ocean, in the terrestrial, that is land. So they form a chemical transformation. They transport, and then they have a chemical transformation. For example, volcanoes, they are emitted sulfur dioxide emitted, and then it get reacted and form gas to particle conversion in the sulfate type of aerosols. The sea salt, the sea, and it goes in the atmosphere, it was a sea salt aerosol, and then it moves from one system to another system, influencing the terrestrial and the marine nutrient cycle also. Now, lastly, the radiative properties. Now, this shows that how the incoming solar radiation, when it interacts with the aerosol, as I said, the scattering and the absorption happens, and this will affect the upward flux, that is upward flux going from the atmosphere, from the surface to the atmosphere, the changes. And this net aerosol effect depends on the balance between the scattered induced cooling and the absorption induced warming. In the climate change process, the it is driven by, as I said, it is direct and indirect. The natural and the human activities influence the direct and the indirect changes in the climate agents, like for example, greenhouse gases, the aerosol, and the clouds. And such changes affect the climate system through the radiative forcing and the non-inertial radiative effects, for example, the changes in the atmosphere dynamics and the cloud physics. And this biological, as I said, biogeochemical feedback also goes in the direct and indirect changes. And overall, these feedback can amplify or dampens the climate process or the climate change. So we all know the IPCC, the Intergovernment Panel on Climate Change, and they come out with a report giving the overall relative effects or the relative forcing given by different components. Gases, you very well know. I don't want to repeat it again. That of course the more positive forcing, that is positive warming forcing or the warming effects are more due to the gases like carbon dioxide, methane, nitrous oxide, chlorofluorocarbons, etc. And coming to the aerosols, that is the SO2, the organic carbons, ammonia, they have a net cooling effect, and mainly through the cloud interactions. And of course the black carbon has a warming effect. And of course these, when they also give changes to the global temperature. So these forcing have an effect on the global temperature. So overall, that aerosols offset a significant fraction of the greenhouse warming. So there is a certain offset by the aerosols. But of course, these are very highly uncertain. They uncertain in forcing. They are highly dynamic in nature. So their measurements also is very important. From one place to another place, highly temporal measurements are required because their uncertainty is also very, very high. So as I said, the measurements are very important, and the measurements can be of from different platforms. It can be from the ground observations. Then it can be through the airborne. Airborne, for example, it can be through balloon experiments or through radio sound experiments, and also through the satellite data. Now, coming back to the impact. Now, the impact is because the air pollution is directly related to the human health and human diseases. And for example, the aerosols, as he has divided here, two impacts. One is the environmental impact, and one is on the human health impact. And I have already discussed the toxicity, that is how important it is, and how negative adverse effect it has on the human health. Now coming to the environmental impact, as I said, the changes the cloud properties, that is the microphysical properties of the cloud. Of course, the monsoon circulation, because if there is absorbing aerosols, they have a different impact on the precipitation cycle. If it is absorbing type of aerosol, or sorry, scattering type of aerosol, it is having a different effect on the precipitation or monsoon cycle. Of course, the it has an effect on the crop yield, the productivity in the ocean productivity, on the terrestrial productivity, and it can cause droughts or floods. Of course, the absorbing aerosols, when it deposited on the ice and glaciers, it absorbs and decreases the albedo, and the melting of ice happens or glaciers happens. Of course, the visibility, that creates a lot of problem, not only in the transportation and aviation sector, but also it is a loss to the property and loss and financial loss. Of course, the damage to the environment and aesthetic effect because of the buildings, the historical buildings, and then there is, because it has a secondary reactions, it reacts and it corrodes many of the our important historical buildings. Now coming to the health effect, that is there is a short term and long term exposure, and the short term is around 48 hours to 72 hours to 3 days if you are exposed to a highly polluted region. So it happen the first impression is irritation to the eyes, nose and throat, then inflation of the lungs tissues, and the some of the asthmatic problems and so on. And when the people are exposed for a long duration, it creates a chronic disease, asthma, bronchitis, the chronic pulmonary diseases, the pneumonia, there is a different respiratory problems, cancerous problem, diabetic, type 2 diabetes also is being reported by long-term exposure of these pollutant, by this pollution. And then the premature deaths, that is children less than 5 years of age, they are mostly exposed. And then the pneumonia in this, because it is malfunctioning or the choking of the lungs of the younger children. And pneumonia is being reportedly high in the children less than 5 years of age. Of course, pregnant women and so on. There are many adverse effects, health effects to the long-term exposure of the air pollution or the aerosol particles. Of course, this has become the hazardous phenomena, because all over the world we see some of the news that this has choked many of the cities. There is a gas chamber. There are pollution episodes, months together, years together, and for a longer duration, and many parts. So it's not only in India or other, but it's a whole world issue. And there are many steps taken by the different governments to monitor, to understand, and to minimize the pollution. Of course, when we say that the air pollution, the if we say the worldwide annually, around more than 12% of the annual deaths are reported from the air pollution, and it is the second highest killer in terms of the annual deaths reported by directly or indirectly by to the air pollution. Around more than 8 million people die worldwide due to this pollution, and on the annual basis it is increasing. And it is reported that the 96% of the pollution deaths are from the PM 2.5, and rest is around 4% is due to the ozone, that is the tropospheric ozone, surface ozone. And in this 96% deaths, that is around 7.8 million deaths due to only the PM 2.5, 60% or more than 60% share is from the outdoor pollution. So pollution can be two types. One is outdoor pollution, indoor pollution. So more than 60% pollution deaths are due to the outdoor pollution, and around 35 to 40% is due to the indoor pollution. Of course, the positive fact is that indoor pollution deaths have decreased over recently 7 to 10 years due to different steps taken by government of different countries. Particularly in India also, there are different steps, positive steps taken by the government and different agencies to curtail that, and around 35 to 40% decrease in the deaths of the household air pollution have reported. But the problem lies in the outdoor pollution. And if you see that the 96% of the deaths due to the PM 2.5, more than 50%, that is around 55 to 58%, is reported from India and China. So around more than 2 million people deaths are reported in these two countries, and these are very severe in nature. So if I say in totality, see, the around 30% deaths are reported from the respiratory functions infections. Around 27 to 28% are from the chronic heart diseases. Around 48% deaths are reported from the chronic pulmonary diseases, and these are in severe in nature. When I say that premature deaths, because this decreases the mortality, this decreases the year, the loss of life. The how much years of life are lost, or how humans die before their age. So if they are exposed to long term highly polluted environment, so their life is also reduced. So it is reported annually that worldwide, that around 3 to 7 years there is a loss of life. And there are certain regions where the loss of life is more than 11 years. If you see the South Asia, the Africa region, the people living in the highly polluted regions, their loss of life is much more above the average of the world. And also the air pollution, there is a loss to the economic activity, or the economic cost. There is a loss. Now it is estimated that the over India, around 1% we are losing every year annually, 1% of our GDP. That is the loss, economic loss to due to the air pollution. Now as I said, the government has also taken initiatives to understand, or the measure the different air pollution levels. And once we measure it, and then the actions, suitable actions, and has to be taken, can be taken. So there are different guidelines. So these are known as the National Ambient Air Quality Standards, and where these standards are categorized in different sections. And they are for example, there are 8 criteria pollutants. That is, these are these pollutants define the air pollution in the atmosphere: PM10, PM2.5, nitrogen dioxide, ozone, carbon monoxide, sulfur dioxide, ammonia, and lead. This is a metal, rest are your gases. And in the out of 8, any 3 can be measured to find the pollution index, which is known as the air quality index. And in any of the measurements, PM or PM10 or PM2.5 is a must to measure. Now what does PM, as I said, this affects your upper respiratory tract or respiratory system, and it gives a lot of irritation and allergy kind of thing. PM 2.5, as I said, it penetrates deep into the bronchial and your lungs, and then it slowly goes in the blood streams, and it causes the chronic diseases in terms of the pulmonary or heart diseases or any other diseases, which leads to mortality. NO2, this also chokes the air, passes through your throat and it creates an asthma. And this is also a precursor for formation of the ozone, which is also a secondary type of aerosol. Ozone is a strong oxidant, damaging it damages the lungs tissues. And also, as I said, it affects the your crop and forest productivity, marine productivity also. Carbon monoxide, it reduces the oxygen flow in the bloodstream when we inhale CO2, and when it goes above the above the standard range, it chokes the oxygen delivery in the blood system, and it causes dizziness, headache, these kind of symptoms. And also prolonged prolonged exposure can lead to the cardio stress. Sulfur dioxide, it causes the bronchial congestion, and there is a breathing problem also it creates. And these are the source for the sulfate aerosols, and which when goes in the higher altitudes can create reduction in the visibility and cooling effect. Ammonia, ammonia is again there is a problem. It creates a problem for the respiratory tract, and it gives a irritation to the skin and the eyes, and this is also very poisonous. Of course, lead is a metal, but when it dissolves, it also creates what you called as a brain functioning, malfunctioning of the brain and also the kidney. And Okay. Now, there are some standards given by World Health Organization. These are the National Air Quality Ambient Air Quality Standards. Uh, they have been revised in 2021, that now the 24-hour average is should not exceed 10, and annual average should not exceed 5. And if it exceeds, they are categorized in different sections. Like for example, this is if it is 10, it is good, and above 10 it will be satisfactory, moderate, poor, very poor, and severe, like that. uh, US has adopted another air quality standards, which is daily 24 average, it is 35 PM 2.5, and PM10 is 150. India has adopted national air quantity standards as PM 2.5 as on an average 24 hour is 60, it should not exceed 60. If it is beyond 60, it is said to be in a good or satisfactory range. And if it is exceeding 60, these are in different ranges like these: moderate, poor, very poor, or severe. And PM10 less than 10, 100, it is as satisfactory, good, and above 100 it is categorized as moderate, poor, and very poor. And then, using the measurements of these air criteria pollutants, we calculate the air quality index, that is what is the quality of the air. And these are also categorized according to these ranges: good, satisfactory. And if exceeding, if AQI exceeds 200, it is known as poor, very poor, and severe. And it is estimated that if suppose there is increase of 10 microgram per meter cube, that is 10 microgram per meter cube of PM 2.5, if there is an increase, it can create and risk in the health, that is cardio or pulmonary disease, by around 7 to 8%. So there is a mortality risk. If 10 units of PM 2.5 increases, so that risk on the health increases by around 7 to 8%. And this causes a lot of problem worldwide. Okay. So I think we have understood the overall concept of aerosol, the optical properties, the different kinds of properties, what is the formation, and what are the health impacts. Thank you very much. So welcome back. So we are open to the questions and the clarifications from your side. One such question we have received, that reference to sulfate aerosols and black carbon. Explain why aerosols with similar sizes can have opposite climate impacts. So, as I said, that the aerosols are classified by sizes, right? So, if you have similar size, what it means, that the size is same, but the seed, that the core can be different. So this the aerosols are classified from their sources. If the similar size of aerosols are emitted from volcano, it can have a core of sulfate. If the similar size of aerosol are emitted from the biomass burning or the fossil combustion, it can have a seed of carbonous aerosol, a carbonous particle. So the nature will be different. The carbonous aerosol will absorb the solar radiation, while the sulfate type of aerosol will scatter the aerosol. So then it will have a different impact, because the earth radiation budget, it will change. So size is one type, but the chemical composition is very important in understanding the radiative effects in the earth climate system. So we are waiting for a few more questions. Okay, so there is one more question. Radiative forcing from biogenic sources can be both climate warming and climate cooling. Yeah. So the biogenic sources, though, what do you mean by biogenic? So I have not touched much upon the biogenic sources. Biogenic sources are the natural sources. For example, pollen grain. So I have discussed on the pollen grains. For example, fungi, bacteria, viruses. So these are all biogenic sources, and these are natural sources. So the radiative effect is all the scattering in nature, because these are natural sources, and they have relatively less impact on the when they interact with the solar radiation. So more of the health impacts they have. So they dissolve in the ocean, that is biogeochemical cycle. They have effect on the terrestrial ecosystem and on the human health. So the radiative impact will be less, because their core, that is the material with which they are made, is not much interactive with the electromagnetic radiations. Okay, now we have one more uh, explanation of scattering, absorption, and extension of aerosol in more simpler words, because I don't get. Okay. So as I said, what is scattering? That is, scattering is the energy which is impacting on the particle, and then it changes its direction. The energy will be conserved while the direction will be changing. While absorption, the energy is absorbed by the particle, and then it is re-emitted in a different energy spectrum. And extension is the cumulative effect, that is addition, I can say in simple mathematical word, that is scattering plus absorption. That both phenomena put together is known as the extension. So as I said, the single scattering albedo, that is the how much amount of radiation is scattered as compared to your extension, that is total scattering and absorption, from it how much is scattered back. So that's the best simpler word I can explain in for your extension. Okay. How how does refractive index affect scattering and absorption? Yeah, so if you remember the slide which I showed, mathematically also it was written that the refractive index, what is refractive index? Refractive index is, that is when the light passes from one medium to another medium, there is a change in the speed, right? Because there is a density, there is a change in the density. Now, the refractive index is denoted by the real part and imaginary part. So if you have a higher number in the imaginary real part, it means that the particle is predominantly dominant in the scattering in nature, while the imaginary part denotes that the particle will have predominantly absorbing in nature. And if we have a mixing of these two, because in nature you don't have a either of these two. Sometimes you have both these two, so you have a both number. It means the dominance will be of scattering, or dominance will be absorbing, but also it will have a scattering nature. So brown type of smoke or brown aerosols, these are organic aerosols, they have a absorbing as well as your scattering nature. Okay. So elaborate on the little of aerosol, why it is called aerosol. Is it the material that is made up of 99% air? No, no, no. Because as I said, the atmospheric composition, 99% is made up of your gases, that is your predominantly nitrogen and oxygen, and 1%, less than 1% is your trace gases. But only 0.1% is made up, is your variable quantities like aerosol and water vapor. Now in that 0.1%, these particles which are known as aerosols are present in the atmosphere. Now, what are aerosols? As you said, title of aerosol, why it is called aerosol? See, aero and sol, air. So, particles present in the air. These particles which are larger than the molecules, that is gas molecules, that is 0.001 to 100 micrometer. That is, these particles are larger than your gaseous molecule. So, these particles, a family of these particles are known as, called as aerosols, and different names you can say. As I said in the slide, fumes, smoke, fog, dust. So these are the different names, and these names are categorized according to the sizes like PM10, PM2.5, and PM0.1. I think we have taken all the questions, and hope it was a useful lecture, and the doubts were cleared. Yeah, thank you.
So welcome back. Now we have the second session with us. We have Professor Neeraj Rastogi from Geosciences Division at Physical Research Laboratory. It is my pleasure to briefly introduce Sir to you to the audience. Professor Rastogi's research focuses on atmospheric aerosols, including their characterization, chemical processes, isotope tracing, aerosol oxidative potential, and brown carbon studies, as well as investigations into upper troposphere, lower stratosphere chemistry using balloon borne and aircraft measurements. He brings extensive academic and research experience, and his work has contributed significantly to understanding atmospheric composition and processes. Sir, we are grateful to you for agreeing to deliver a talk to our audience, and I also welcome you to this workshop. Over to you, sir.
Okay, thank you. Thank you very much, Dr. Mehta. So before I start, I wish to thank the organizer for giving me this opportunity so that I can share whatever little bit knowledge I have acquired over the years with all the viewers at present. So as you all can see, the topic of the talk is importance of aerosol chemistry in air quality, climate, and health. And before I start, let me just tell you a little bit about the PRL. I come from Physical Research Laboratory, which is also known as the Mother Institute of ISRO. I would encourage whenever you find time, you go to the website where we work, ranging from the interior of the Earth to the end of the universe. So whenever you find time, just visit PRL website and you will see that we do wide variety of work. But today we are talking about aerosol chemistry, so I should continue with that. So before we go to aerosol, let us first talk that what are the things we have in the atmosphere. See, this figure I like a lot, which is from this particular paper. Here, the size range which are present in the atmosphere are given. What you see here, we have sizes from 100 picometer to 10 centimeter. And this whole range is 10 raised to power 9 orders of magnitude. Just imagine this, what is the range we are talking about, which is present in the atmosphere. And they are all connected. So in principle, whatever you have as a gas molecule can convert to aerosol, then further become as a cloud condensation nuclei, make cloud, make snow, cropper, and come down. So that means this particle can come in the size of this particle. There's a possibility of that in the atmosphere. Now, here you see the different colors also. So gas, for example, gas molecules are in the gray. Then you see the range from 1 nanometer to 100 micrometer. This is the aerosol size range. And based on size, they are called ultrafine, fine, or coarse. I will be talking a little more about that in a few minutes. This size also depends upon how they are coming in the atmosphere. So if it is dust derived or sea spray, they are usually coarse in size. If they are from secondary formation processes, they will be sulfate, soot, secondary organic aerosol and all. They will be in ultrafine or fine mode. Then there can be a variety of bioaerosols like pollen, spores, bacteria, viruses, protein, and their size range. You can see them here. They act as cloud condensation nuclei. So this is the size range given. And in the form of precipitation, when they are coming down to Earth, it can be in the form of rain, snow, graupel, hail. And this is the size range we are talking about. Now I'm keep saying size range, size range. If we just would like to imagine what we are talking about, the size range we are talking about, see, it is an analogy. Huh? So if we consider the minimum size as one ant, which is about 3.5 millimeter, then maximum size is moon, which is 3,500 kilometer. So that means from ant to moon, all this I'm taking as an analogy. They are present in the atmosphere. This is the size range we are talking about. If we talk about the aerosols, they vary from 1 nanometer to 100 micron. And if we talk about the size, again, visualize about the size of these aerosols. It is like if you have a smaller size as a coin of 10 rupees coin, then the biggest size will be a big crater, 3.5 diameter crater, which is this, I just put a figure like a Ramgarh crater from Rajasthan. So this is the size range we are talking about. Okay. Now, in actual terms, if you want to understand what is the size we are talking about, so 100 micron is about the diameter of your hair. Or if you take a pin, the point of the pin is about 50 micron. So now you can visualize which size we are talking about, and we will be dealing about with this during this lecture. Now, multiple times you would have heard the name TSP, SPM. TSP is total suspended particulate. SPM is suspended particulate matter. Then you must have heard PM10, PM2.5, PM1, PM.1. So what does that mean? So if you consider all the particles from 1 nanometer to 100 micron, they will called as TSP. If you talk about the particles 10 micron and below, then it is called PM10. If we talk about 2.5 micron and below, you will call it PM2.5. If you call it 1 micron and below, PM1, same way, PM.1. So that means all these three are the subset of PM10. PM1 and PM.1 are the subset of PM2.5. Okay, so this you will keep in mind when we are discussing further. Okay, going ahead. So before I proceed, let me just tell a little more about it. So by definition, what is aerosol? What do we mean by aerosol? So solid or liquid particles suspended in the air, they are called aerosols. As we saw, that size can be there can be large variability in the sizes. They come now from where they are coming from. So they can come from various natural sources like sea salt. Many of you may be living around the sea, or you would have gone to the coast. You would have seen this whenever you are around, you see salts on your skin, which is coming as a spray from the sea. So that is sea salt actually. If we see around again, means if you have a dry loose dust in the surrounding, strong winds take the dust in the atmosphere, that is mineral dust. Volcanic eruptions, it is not a continuous source. It happens once in a while, but whenever it is happening, it put huge amount of aerosol in the atmosphere. Then biogenic emission, variety of pollen, spores, etc. They are coming from biogenic sources, and then these plants also release VOC, which is volatile organic carbon, which convert into aerosol. So that is the source. Then forest fire, once in a while they happen. So these are all natural sources of aerosol. Now, others are man-made. Man-made or anthropogenic, both are same thing. So what are they? So it can be industrial emissions, you all know. It can be vehicle emissions. You are from different cities, you see the vehicles around and you see the pollution coming out of it. Biomass burning, which you know every year it happens in Punjab, Haryana, and into a gastric plain. And then we also burn wood and all. Winter season is here, so in order to keep us warm, we always use often use wood or coal or something. Then we have thermal power plant, which use huge amount of coal. And then cow dung cake was used as a fuel for cooking. Now means with the more and more um, uh, from government side, Ujjwala Yojana and all, from because of those, this cow dung is reduced, but still it is used in the rural areas. So these are the major sources. Size already we talked about, it ranges from few nanometer to several microns. Source emit primary particles as well as precursor of secondary particles. What does that mean? Primary particle means aerosol are coming as a particle from the source, like mineral dust or pollen or sea salt. Secondary particle means sources did not emit the particle. They emitted the gases like sulfur dioxide, NOx, or volatile organic carbon. But in the atmosphere, they got oxidized, they form sulfate or secondary organic aerosol, and then they become the particle. So they are called secondary particle. Now, if we talk about the lifetime of aerosol in the lower troposphere, it is just about a week. So one can think, okay, means it is just going to stay there for a week. Why you are worrying about? Let them be there. So we will see why we are worrying about. But before proceeding further, we talked about the sizes. Now, in terms of chemical, if you see, what are the species we have? So we have variety of carbonaceous compound, that is carbon containing compound, which has a oxidation state ranging from -4 to +4. For example, you have methane, which is the oxidation state of -4. Then NMSC means non-methane hydrocarbons. Carbon. AVOC is anthropogenic volatile organic carbons. BC is black carbon. POA is primary organic aerosol. SOA is secondary organic aerosol. Primary, secondary we discussed in the last slide. Then BRC is brown carbon aerosol, carbon monoxide, CO2. So all these are carbonaceous components present in the atmosphere. And when we talk about the organics, there are thousands of organics. Means multiple PHAs or carboxylic acid, sugars, alkanes, propanes, multiple type of organic compounds are there. Then you have variety of nitrogen containing compounds. The oxidation state varying from -3 to +5. For example, ammonia, nitrogen, N2O, NO, HONO, NO2, HNO3, HNO3, nitrate, and some concentration of radicals like N2O5 and NO3 radicals. Then you have sulfur containing compound, again oxidation state ranging from -2 to +6. What are they? The H2S, and then dimethyl sulfide, carbon disulfide, OCS, SO2, sulfate, etc. Then you also have variety of halogen containing compounds like chlorofluorocarbons, hydrofluorocarbons, halocarbons, etc. And then you have ozone. Ozone is maximum concentration about 90% present in that stratosphere, which is saving us from the dangerous part of the sunlight coming from the sun, that is UV light. And then you also have ozone in the troposphere, which has a large variability in the concentration depending upon various sources and processes. And then you have other things like sea salts. We talked about the among the sources. So sea salts can have sodium chloride, sulfate, magnesium, calcium, potassium, etc. You have mineral dust, which can have calcium, magnesium, sodium, potassium, iron, aluminum, manganese, silicon, etc., etc. You can have variety of anthropogenic metals from variety of industrial process or various combustions like lead, zinc, chromium, copper, cadmium, nickel, vanadium, etc., etc. So these are the some of the compounds present in the atmosphere when we talk in terms of chemical species. So now we know in terms of size what range we are talking about, and in terms of composition what we are talking about. So what are the things which can be present in the atmosphere? Moving further, so once aerosols are in the atmosphere, then they can also undergo variety of transformation process. What does that mean? So now we already know that we have variety of aerosol like organic, salt, metal, dust, etc. So it is there in the atmosphere. Then you have some relative humidity. Accordingly, you will have some liquid water content which can condense at the surface of aerosol. Now you have water and aerosol both together. Depending on temperature, water can be more or less. Then the gases in surroundings can diffuse in this water. These gases like VOCs, NOx, ammonia, and sulfur compounds. And then by reacting with variety of oxidants present during nighttime or daytime, like hydroxyl radical, hydrogen peroxide, ozone, nitrate radical, etc., these gases oxidize and form secondary aerosol like sulfate, nitrate, secondary organic aerosol, variety of secondary brown carbon. So because of these transformation process, the changes, when there is a change in characteristics, so physical, chemical, optical, and isotopic characteristics. What does that physical means? Size and so if again you recall, I was saying that 100 picometer gas molecule can come back as 10 centimeter hail, come back. So this changes because of this transformation process. So size is changing. You have aerosol, things are condensing. So in a way, you are increasing the diameter of this particle. So you are changing the size. Initially, this was hydrophobic in nature, but when you are coating, you are making it hydrophilic. So it is changing the surface properties. Initially, it was absorbing. Now with the coat, you are coating with the scattering type of species. So you are making it complex. So you are changing the optical properties. You can also change the toxicity of these aerosols. So initially, they were not so toxic, but because of these various processes which are happening, because depending upon aerosol pH and all, they can become more and more toxic when they are in the atmosphere. And then it also changes the bioavailability of nutrients. What it actually means, we will be talking about, but that time just keep in mind what I have said this here. It changes the bioavailability of nutrients. In the last, we were talking about this. And then if we talk about the removal process, they come out from the atmosphere by two major processes, dry deposition and wet deposition. What is the dry deposition? Which happens around the year. It is sedimentation, diffusion, impaction, absorption, and it can happen on soil, water, plant, or any other surface. So for example, if you are at your home or office, wherever, you put your finger in the surrounding and you see some dust in your hand. From where it is coming? It is through the dry deposition of aerosol from the atmosphere. And then they can also get removed from the atmosphere by wet deposition. So we know that things are very polluted, but once rain happens, you see things are quite clear because rain cleans the atmosphere or aerosols from the atmosphere. So this is complete the cycle. Now we know the sources, we know the transformation process, we know the removal process. So, okay, we know all these things. So how does it matter? Means why it matters to us? So what are the effect of ambient aerosol? So let us now talk about some of the effects of aerosols. It affects our climate. How it is affecting our climate? See, it because by affecting it radiation budget. What is that? So we know that energy is coming in from the sun and going out of the earth. And if things are in balance, temperature is maintained. If somehow we can increase the incoming energy or decrease outgoing, it will it will warm the earth. If you do opposite, it will cool the earth. So aerosol actually does that. We will be talking a little more about that in a coming slide. Same way, it affects hydrological cycle because they act as a cloud condensation nuclei. What does that mean? See, we know water vapor coming from ocean or any water body, it is evaporating water vapor is having the atmosphere, and it is coming back as a rain. But cloud cannot form if you don't have aerosol. Aerosol act provide the seeds for cloud. So you have to have seed to make cloud. They provide surface to what for water vapor to condense on. That is how they affect the hydrological cycle. Little more we will talk in a couple slide. Then it affect air quality. So if you are in any city, you can see this kind of haze around. It is because of aerosol. If looking from the satellite, this is Bay of Bengal, this is Indo-Gangetic Plain. From satellite, you can see how thick layer it is there because of aerosol. It affect our human health. Human health it is affecting because it is in the air. We inhale, air goes in. Along with that, aerosol also goes in and affect us in a variety of ways, which I'll be talking about. It affect atmospheric chemistry. As I said, for the water vapor, for gases also, it provides surface. It is like you are giving playground to the players to play. So players are these gases, playground is aerosol surface, and then when they play, they make a variety of things and affect the various atmospheric processes. Then it also affects aquatic ecosystem, how it is affecting. So we talked about aerosol sources and removal. So if these aerosols are getting removed over remote ocean or lake, so in a way they are acting as a supplier of nutrient to those lakes or ocean. So nutrients like nitrogen, phosphorus, iron, etc., they come from the aerosol to the surface of the ocean or lakes. This also I will be talking in detail in the coming slide. And they also affect acid rain. Acid rain in India, it is not too common because the soil we have, it is very calcareous, which is alkaline in nature. So it utilizes the acidity in the atmosphere. But if you go to Western world, there are multiple places, acid rain is common thing. And it is because of the acidic species like sulfate or nitrate present in the atmosphere. Okay, so when we are talking about any of the effect, size and composition, both are very important. I was looking the previous presentation also by Professor Yogesh Kant, and he was talking about how size is affecting the various optical properties and all. So size is important, and composition is also important because somebody asked that whether sulfate or black carbon, some same size of particle, but sometimes it is scattering, sometimes it is absorbing. So that is the composition of aerosol, surface properties of aerosol, which is causing that kind of effect. And atmospheric processing affect both size and composition, as we have saw in transformation slide that because of the processing, size was initially something else, but it can change. Surface property was something else, it can change. Optical properties was something else, it can change. So processing affect the composition. Okay, now moving further. So if these are aerosols are present in the atmosphere, how do we measure them? Okay, so they are measured by through a very wide variety of things ranging from ground-based sensors to polar and geostationary satellites. Satellite portion, I think in the next talk, it will be covered. I will be talking about mainly ground-based studies. Okay, so how do we do that? So there's something called offline sampling. Offline sampling means you take the sampler, like high volume sampler, to whichever place you want. You go there, you collect aerosol. This is the filter before collection. This is after collection. So this is means whatever aerosol you have collected on a filter, it looks like this in a dirty place like Ahmedabad or Delhi or Kolkata like that. And when we say high volume sampler, you see it is high volume is flow rate we are talking about. This is 1200 liter per minute flow rate. Then you can also use low volume sampler, which has only have 17 liter per minute flow rate. It uses a small filter. It is 47 diameter, and this is 8 by 10 inch. It is like a paper sheet. This filter, and this is just a circular punch of 47 millimeter. So once we have collected this aerosol, okay, these are the two high volume and low volume. Then you can also collect using cascade impactor. Cascade impactor means size segregated. Here it can collect TSP, PM10, PM2.5. Now we know the meaning of if we say TSP, if we say PM10, PM2.5. I already said in the beginning what does that mean. So these samplers are for collecting TSP or PM10 or 2.5, etc. This sampler you can collect different size at different stage separately. There is a flow of air, so all the particles you are pulling with the same flow rate, so bigger particles impact first, and then you move them around, so smaller particles go further and then impact other plate. So that is how at different plates you collect different size of particles, and it has a flow rate of about 30 liter per minute, and it collects like this through impaction. This is filtration. We are filtering the air through the filter. Here it is by impaction. Okay. So now these are the sampler. Now aerosols are sampled outdoor open air at a site. Means site you decide. So where you want to collect aerosol, you can collect in Delhi or in big cities or in rural areas, or you can go to very remote place like Arctic or Antarctic. So there means wherever you want to take, you can take this sampler, collect the aerosol, bring it back to your lab and analyze and know the composition. How long you will run the sampler, that depends upon the concentration of aerosol over a given site. For example, if you are at Delhi, a few hours of sampling is sufficient. But if you are at, say, Arctic or Antarctic, you should collect it for a longer time, say 3-4 days, so that you have enough sample on the filter to analyze. Okay. So now by whatever sampler, by whatever you have collected filter, now you are coming to the lab with the filters. So then what you can do wide variety of chemical analysis, like water soluble inorganic species. When I say that, I mean we are talking about ammonium, sodium, potassium, calcium, magnesium, chloride, nitrate, sulfate, etc. You can measure trace metals like lead, arsenic, cadmium, copper, chromium, nickel, vanadium, etc., etc. You can measure water soluble organic carbon, water soluble total nitrogen, bulk organic and elemental carbon. Organic speciation, when I'm saying organic speciation, it means you can measure polycyclic aromatic hydrocarbons, alkanes, hopanes, dicarboxylic acid, levoglucosan, etc. Then you can measure brown carbon. You can do the speciation of brown carbon. You can measure oxidative potential. What does that mean? I will be talking about it later. Then you can do stable and radioisotopes. This is for very specific type of studies. And then you can measure, now this is very new thing, you can measure micro and nanoplastics also in aerosols. So once you have sample, you can do all wide variety of things. How do you do that? So for organic and elemental carbon, you use this organic and elemental carbon analyzer. For major ions, you use this ion chromatograph. For organic speciation, use GCMS, gas chromatograph mass spectrometer. For metals, you use inductively coupled plasma mass spectrometer, SPMS. For TOC and TN, you can use TOC-T analyzer. For brown carbon, you can use liquid wide capillary cell along with the portable UV spectrophotometer. And then people can also measure the things, aerosols, using online measurements. So what are online measurements? So what is the difference between online and offline? So previously, whatever I was talking about, you have taken the sampler, you collected the sample for say 8 hours, 10 hours, and then whatever you collected in 10 hours, you are bringing back to your lab and then analyzing. Online means it is continuously measuring. So every minute you have the data. So this is online measurement. So for some examples are this EBAM, which is called Environmental Beta Attenuation Monitor. This is for the mass concentration of aerosol. Now, this low-cost sensor are very popular these days. So because of they are cheaper, so multiple sensors can be put across the city, and then you can measure the mass at different places. If you are interested in number and size of the particles which are present in the atmosphere, you can use instrument like scanning mobility particle sizer, which is called SMPS. If you would want to do chemical speciation online, so you can use aerosol mass spectrometer. which does the non-refractory organics and inorganic species. You can use ZACT, which measure metals in the atmosphere. You can use ethanometer, which gives you the black carbon concentration in the atmosphere. So these are all at the ground level. But if you are interested in looking at the broader scale, on bigger scale, then you can use passive or active remote sensing, bipolar and geostationary satellites. Okay, moving further. So I was talking about, now I will be telling you that why aerosol composition is important in any effect of aerosol we study. So here if you see, I was telling this is the radiation coming in, going out, things are balanced, everything is okay. But then you put aerosol in between. Now these aerosol, they can scatter the incoming radiation, depending upon if they are sulfate, nitrate, organic type of things. They can absorb the incoming radiation, which particle can absorb, like black carbon, brown carbon, dust type of particle. If they are absorbing, they will warm the earth. If they are scattering, they will cool the earth. Same way, I told you that aerosol act as a cloud condensation nuclei. So once you make the cloud, cloud is scattered back the incoming radiation. So indirectly, you are scattering back the radiation because of the aerosol. So that is called indirect effect. And this cloud condensation nuclei also means how good or bad cloud condensation nuclei aerosol can be. That depends upon the surface property of those aerosol. For example, hydrophilic species are effective CCN. What does that mean? Say, suppose you have ammonium sulfate kind of particles in the atmosphere. They are hygroscopic. They will try to attract more and more water vapor towards them. They will make the cloud droplet, and then the more water vapor they will attract, they will make rain droplet and fall down. But at the same time, if you have hydrophobic species like mineral dust or black carbon, they will repel the water vapor. They will not allow easily to form the clouds, or even if it is forming, it will not allow to grow. So that is how it can affect the cloud lifetime, and it can also affect the precipitation. So hydrophilic species positively affect precipitation, and hydrophobic species negatively affect the precipitation. So depending upon different type of aerosol, effect of they affect the earth radiative forcing. Mostly it is negative forcing, means it cools the earth. So on average it cools the earth, but they have many adverse effect also, which again we will be talking about in the coming slides. So now let us talk a little bit about the aerosol and rain. So I like this paper quite a bit. So this is by Coren et al. In Nature Geoscience. So Coren et al. Examined the relationship between aerosol abundance and rain rate. What is the meaning of rain rate? Say, means sometime whole day it is raining very slowly. Means whole day rain, but just 10 millimeter, 20 millimeter, whole day rain. Sometime within half an hour it is 20 millimeter. And sometime the cloud burst happens. That means huge amount of rain falling in a very short time. That is cloud burst. So that is rain rate. Rain rate can be less, or highest rain rate we discussed is cloud burst, and lowest it can be few millimeter for the whole day. So these people have assessed the relationship between aerosol abundance and rain rate, which is a key factor in climate and hydrological process. And they use satellite data. What they did, they took the rain data from tropical rainfall measurement mission, which is called TRMM, and they took the aerosol and cloud property data from MODIS, is moderate imaging spectrophotometer from NASA satellite, and they got the meteorological information from global data simulation system. And what they found, that now you see these boxes, they are over land also, they are over ocean also. So now, and these, see this plot from these different boxes. This R is rain rate, millimeter per hour, and AOD is aerosol optical depth. Aerosol optical depth is a kind of measure of aerosol abundance in the atmosphere. So what you see, that as aerosol AOD is increasing, rain rate is also increasing at different places. But this red and blue difference is, red is when, means you remove the grid where there was no rain during that time, and blue is when you include everything. But in both the cases, you see there is a positive relation between AOD and rain rate. Then the question comes, why it is happening? So increase in aerosol abundance were found to be associated with the local intensification of rain rates over both land and ocean. However, if you talk about the mechanism, it is yet to be understood. This is just an observation. Okay, moving further. This is quite interesting thing because we all care about our health. So what is aerosol and health? See, from for long time, it is known that aerosol affect our cardiovascular system and respiratory system. When I say cardiovascular system, it means it affects our coronary artery disease. It can cause coronary artery disease. It can cause heart attack. It can cause stroke, blood clots. Respiratory system effect means it can cause COPD diseases, asthma, lung cancer. But there are growing evidences that the air pollution effect are much beyond only these two. What are the other effects people are looking now? It can affect our brain. And we are talking about the air pollution. Is affecting our brain. It can cause Alzheimer's disease or cognitive decline. It can affect our nervous system, cause Parkinson's disease and other neurodevelopment disorders. It can affect our renal system, which may cause various kidney diseases. It can affect our endocrine system, which cause obesity or diabetes. It can affect our reproductive system, which can diminish fertility. It can premature death, birth. It can affect low birth weight. This, you see, it affect embryo. That means soot particles are found in the lungs of a in means in embryo. That means children which is in the form of embryo, it is not yet born, but soot particles are there. That means your air pollution is affecting us before we are born. And these effects can be acute or chronic. When we say acute, acute means immediate effect. That means something toxic you have taken and you are seriously ill or dying. So that is acute effect. Chronic means slow poison. That means very slowly, every day you are taking a small amount of poison, so which is actually affecting your health and also it is reducing your life. That is called chronic effect. And air pollution mostly cause chronic effect since so you might have seen that whenever there is a too much of pollution in the Delhi, then there is too much of noise that okay means we should do this, we should do that, and once rain happens or something happens, everything cools down. Then nobody worry about. And moderate amount of air pollution is there always, which is causing variety of chronic effects, but they are not assessed properly and they are not taken care of. Now, if we try to little understand how actually they are affecting our body, so now again see variety of size of aerosols are present in the atmosphere. You are inhaling, so all everything is coming in. When while making your body, God has made your nose in such a way that it doesn't allow very big particle to reach in. So it knows allowed only particles smaller than 10 micron in size. That means PM10 only are allowed to go beyond your nose, and they stay up to this region only. So PM bigger particles stay here. If they are further small particles, PM2.5, they can go deeper into lungs. If they are further small, like ultrafine particles, PM0.1 or nanoparticles, they can pass through this our veins and through macrophage, and they can go into bloodstream. We all know that something is in our once it is in our bloodstream, it can reach to any part of our body. And if it is reaching to any part of your body, it can affect you in a different way. It can affect physically or chemically. Physically means it is going at some place and getting sitting there. So it is blocking the blood flow. So it is affecting physically. It can also affect chemically. That means it is not only sitting there, but it is reacting with the cells in the surrounding and causing variety of problems, which we have discussed in the previous slide. How do they affect actually? So it is via Ross imbalance. This is the most acceptable mechanism. There are multiple mechanisms, but most acceptable is this one, that within the body, it disbalance the antioxidant and oxidants. Oxidants are like hydroxyl superoxide, oxygen, iron, hydrogen peroxide, or antioxidant like glutathione, ascorbic acid, etc. So an imbalance favoring oxidants or destroying antioxidants lead to damage, which is called oxidative stress, inflammation, or cell death, and that is how it affects. Now, the capacity of particles or aerosols, the capacity of aerosol to generate reactive oxygen species or deplete antioxidants. In both cases, it will affect the Ross imbalance. That is called oxidative potential of aerosols. Okay. Now I'm just one study from my own work I'm showing here. This is the paper in 2023. And here we did the oxidative potential studies at variety of places, which you can see here. Please look at the bars and pie chart very carefully. So what are the sites? We did the sampling over Arabian Sea via using a ship. We did over Ahmedabad, Mount Abu, Patiala, Kanpur, Shillong, Port Blair in Bay of Bengal. Now again, as I wrote, you see the bars and pie chart carefully. Now we have black bar, red bar, green bar. Black bar is the mass concentration of aerosol. Green bar is the oxidative potential OPV, the oxidative potential with respect to volume of air. And red one is OPM, which is oxidative potential per mass of the aerosol. So just a little bit, we understand what the meaning of OPV and OPM. Say 1 meter, say 1 meter cube of air you consider as the plate of food. So plate can have more or less food, so more or less concentration, more or less OPV you can take. And OPM means whatever food you are taking, per kilogram or per gram of that food, how much per gram is toxic. So that is OPM. So what it means? So sometimes you can eat a lot of food, but it may not be toxic. Sometimes you are eating very small amount of food only, but it can be very toxic. So that is decided by OPM, and amount is OPV. As I wrote, quantity and quality. And what is the inference of uh, this study? The bar which I was talking about, you see, concentration are higher. For example, Patiala mass concentration was very high, but green and red bar are relatively lower than other places. Port Blair mass concentration is quite low. Shillong mass concentration is quite low, but this red and green bar are high. So that means oxidative potential, and these are the sites will receive the aged aerosol. That means via transport things are coming here. So it is in a way indicating that whatever we emit with aging during the transport, they become more toxic. Now you recall the transformation slide I was saying when I was saying it can change the transformation can change the toxicity. And it is changing. What we are seeing, it is changing that things are becoming more and more toxic as they are traveling. So that means you are sitting at a very remote place like Port Blair and Shillong, and concentration is low, but it can be quite toxic as we see. And why it is so? It depends upon the composition. So I will not go in that detail today because as I learned that the audience is from a very wide variety of backgrounds, so I will not go in too much of this composition detail. So overall, what our research revealed that oxidative potential of biomass burning derived species are more than the fossil fuel derived biomass fossil fuel derived species. Oxidative potential of anthropogenic aerosols are more than natural aerosols. Atmospheric aging and fog processing increase aerosol oxidative potential. And aerosol OP is actually governed by the chemical composition of the aerosol, not the mass concentration. Most of the mitigation studies, if you hear about, they talk about the reducing the PM10 mass concentration. Even if you're reducing the mass concentration, if you're not changing the composition, which is actually toxic, health effect will not be there. So that is what it is written here. So mitigation strategies for reducing mass concentration alone may not be sufficient, and linking aerosol oxidative potential with health effects may be a better way for better health. Now I'm coming to the last part of my talk. So I was telling again, if you recall, I was saying that aerosol removal as a nutrient supplier to the remote ocean or lake. So nutrients like nitrogen, phosphorus, iron, they are part of ambient aerosol. And over many oceanic regions, the soluble iron is limiting nutrients actually. So aerosol removal from the atmosphere is actually the major pathway of supply to the phytoplankton in remote ocean lakes. How does it matter? So this phytoplanktons, so if you increase the nutrient, it will increase the CO2 uptake by biological pump, which is phytoplankton. And then they will take it down to the surface of the ocean. So that means in a way you are removing the CO2 from the atmosphere and burying it down to the surface of the ocean. So that means you are actually cooling the earth by the whole process by reducing the carbon dioxide through this biological pump. And just one more example I will take. Don't go in too much detail. Just see what I'm just listen carefully what I'm saying. This is Fe. Fe is iron. So iron total concentration, iron water soluble iron concentration. And these are the lines. And this is log scale. Both are log scale. And these lines correspond to if solubility is 0.01%. This is the line, and solubility is 50%. This is the line. Okay. Now, what is the meaning of solubility? Say, iron, as I said, it is a nutrient. Now, you take 1 kilogram bar of iron and throw in the ocean. So that iron, can it be utilized by ocean? No, because our biology needs soluble iron, not the total iron. So if somehow we can increase the solubility of iron, then it will be much more useful rather than the total amount. And a constant processing of aerosol that can enhance the nutrient solubility. Now, again, if you recall that transformation slide, I was saying aerosol pH and aerosol pH. If you have lower pH, it can dissolve the iron and it can increase the supply of iron that from whatever 1 kilogram bar you have taken, now you are taking the soluble iron from there and then you are supplying. So increased iron solubility means even if your total amount of iron deposition is low over a given region, bioavailable iron can be significant. And if you see different symbols here, PM10 2.5, that now we know the meaning of what is PM10 2.5. BOB means Bay of Bengal, N means North Bay of Bengal, South Bay of Bengal, Arabian Sea is ARS. Then question arises, this solubility depends upon the source or processing. Even is it the processing only affecting the solubility, or sometime water soluble iron can come from the source also? So in one of our study, we have shown there is a covariability of iron and potassium, which indicates potassium is the marker for biomass burning. Since both are going 1 to 1, that means biomass burning could be a significant source of iron, and processing also, as we have seen in this slide. That means both are important. So change, and from this study, this change in solubility was shown to be associated with aerosol acidity over Northern Indian Ocean, which was much higher over the Bay of Bengal than the Arabian Sea. Why is it so? Because when we are in Arabian Sea, things are coming from, say, dust from Middle East. So their dust is coming and directly going to the ocean. But when it is same dust is flying through Indian continent and falling to the Bay of Bengal, then it is getting processed, more and more processed. Processing increasing the solubility of iron, and that is how things from here reaching towards here. So with this, I will summarize what I am summarizing. So aerosol affects our environment in many ways, ranging from air quality and human health to climate change and aquatic biodiversity. Aerosol aging in the atmosphere cause numerous transformations in their physical, chemical, and aeronautical properties, which in turn can modify their assessment of aerosol effects. Studying aerosol chemistry is inevitable. We have seen, means if you don't know the chemistry, you can't talk about the detail. So it is inevitable to properly understand any effect of aerosols. But overall, comprehensive studies of aerosol physical, chemical, and optical characteristics with a good temporal and spatial resolution are important to effectively understand the impacts of ambient aerosol on our environment and then plan appropriate mitigation strategies. And with this, I wish to thank you all for your attention. I used to like, means whenever I find time, I used to put various different information on effect of aerosol on air quality, climate, health, etc. for general public awareness on different social media platforms. So any of you, if you're interested, you can follow these LinkedIn or YouTube. So with this, I wish to thank again. And if there are questions, I'll be very happy to address them. Hello.
Such a wonderful, informative, and enlightening talk. We will break for 2 minutes. Let us compile questions from the students which are coming through different platforms, and then we can have them one by one.
Fine, madam. I'm online. Yeah.
Thank you. So, sir, we have received few questions.
Yeah.
So one question is, can aerosols affect terrestrial crop yield?
Yes. Because as I said, they act as a nutrient and toxicant both. So depending upon what type of aerosol are depositing on crop, they can have the effect. It can be positive or negative both.
Right. So another question is, can artificial cloud developing help in combating aerosol problems?
Okay, this we see in news also. So we should understand one thing. See, we have seen that wet deposition is a major removal pathway of aerosol. But in order to have wet removal, first you have to have water vapor in the atmosphere. Aerosol act as a seed, but seed will not work if you don't have water vapor. So if you have water vapor which is not condensing, then means you can use. But means you can't simply put any kind of aerosol and you expect precipitation. That will not happen, as per my understanding.
Okay, thank you, sir. One more question is why is aerosol impact on climate more uncertain than those gases?
Because of the lifetime. In the beginning, I told you that the aerosol lifetime is just about a week. So things are very dynamic. Unlike aerosol, greenhouse gases have a lifetime of multiple years. So they stabilize and their effect can be more properly assessed. But aerosols, since they are highly variable in time and space, and we have limited measurements, it is difficult to assess them very precisely, and that is why there are more uncertainties. Yeah.
Okay, so one another question is, sir, can machine learning models improve the prediction of aerosol chemical composition by integrating observations from multiple platforms?
So machine learning, AI, it is applicable is now in every field we talk about, and aerosol is not untouched by that. People are trying to do things, but machine learning means you whatever trend you see, you predict accordingly. But things may change in between. So, in addition to machine learning, monitoring is also important to make sure that whatever prediction you are doing is actually going in the right direction. Otherwise, you take midway corrections and then keep improving the machine learning things to use it more effectively.
Okay. So one last question we'll take, sir. This is on, yeah. So, how well do current chemical transport models represent aerosol aging?
Okay. Aerosol aging is least captured thing, I would say, because again, it can be highly variable. It depends upon the liquid water content of aerosol. It depends upon the aerosol pH. It depends upon what type of missing state of aerosol, and which is very difficult when you talk about bottles. You are talking about a very big scale, and things are happening on a very small scale. So this integration is still lacking.
Yeah. Okay. Thank you so much, sir. Thank you for your time and agreeing to deliver this talk at a very short notice, sir. Thank you so much.
Thank you for the opportunity. Thank you very much.
Thank you. Thank you.
Yeah.
Thank you.
Now I will leave. Huh? Okay.
Yeah.
Thank you.
Thank you. So, welcome back to the third session of this workshop today. So far you have learned in the previous two sessions what are aerosols and why are these important. They affect visibility, they affect human health, they affect the Earth's climate system, they affect the biology as well as chemistry of the Earth. They can be both of natural as well as anthropogenic origin. They are so much inhomogeneous in space and time that one model cannot be applicable to the other place, and the distributions are dynamic, they are changing all the time. In fact, the entire science of aerosols, if you look into, is interdisciplinary. So far you have learned about the physics as well as chemistry of aerosols. Now this session will tell you about how do we measure the aerosol properties using remote sensing. So, before we delve into that, first we should understand what are the common aerosol parameters that we mostly study using remote sensing. So, in the first session, you have learned about aerosol optical depth. That tells you the amount of light extinction in a particular total column of the atmosphere. It could be the vertical column, it could be a slant column also, right? So, and if you want to know about how much light is extinct at each level of the atmosphere, this is given by a coefficient called extinction coefficient. Okay, so because it is imperative to understand that, because atmosphere density is changing as we go from ground to the top. So the amount of particles that are lying in a particular layer of the atmosphere will also be changing. So the extinction coefficient of different layers will be different. In total, if you integrate this extinction coefficient over the entire length of the column, what you get is aerosol optical depth, right? So these are the two fundamental physical and optical properties of aerosols. Other properties that you have learned about is single scattering albedo, that tells you how much amount of the light which has been extinct by the aerosols, how much portion of that is being scattered. See, Dr. Yogesh Kant told you about the fundamental aspects which are happening while the light is extinct by the aerosols. What happens is light is incoming and it interacts with the particles of the medium. If these are aerosols, some portion of the light will be absorbed and some will be scattered in different directions. Right? So, how much of that light which is lost by the aerosol has been due to the scattering of light is given by single scattering albedo. So, if you have higher SSA, the range is between 0 to 1. If you have higher SSA, the light is mostly scattered. If you have lower SSA, that means the component of absorption is higher. Then we had also learned about phase function. Phase function is how when the light is incoming and interacts with the particle, in which direction it is going to be scattered. It can be scattered in multiple directions, right? So if it is this entire thing is embedded in the form of phase function, and to give it a number, we have asymmetry parameter. So if the light is mostly scattered in the forward direction, the asymmetry parameter is positive and close to 1. If it is mostly back scattered, then the asymmetry parameter is negative and close to -1. If the light is spherically distributed, light goes in the forward direction also, backward direction also, G is close to 0. So this is another parameter. Then we have also learnt about angstrom exponent. This is very important because it tells you about the size of aerosol. So if angstrom exponent is high, that relates to the smaller particles as in smoke. And if the angstrom exponent is greater, then it shows that the particles are mostly bigger in size. For example, large dust molecules or sea salt particles. Another parameter is LiDAR ratio. See, as these all parameters, optical depth, then single scattering albedo, asymmetry parameter, angstrom exponent, these are largely telling you about how the total column of the atmosphere is affected by which type of aerosols, what kind of extinction, which direction the light is getting scattered, and all that. But if you need to know the information at different layers of the atmosphere, then we need to go for the LIDARs. Okay, so when we'll study more about the LIDARs, as in the first session also you learnt about Calypso. So I'll be talking more about it, but similar to single scattering albedo, there is a parameter that tells you about different layers of the atmosphere, how much light is getting scattered. So if you have low LiDAR ratios, scattering is more. For example, dust particles or water droplets. If you have higher LiDAR ratio, that means the particle in that particular layer is more of absorbing kind. For example, smoke or soot particles. Another related parameter is depolarization ratio. So it indicates whether the particle is spherical or irregular. I'll be talking more about it when we'll learn about the polarization. But important point here is, if the particle is preserving the polarization of the light. See, light can be unpolarized or it can be polarized. So if you are throwing a polarized light, and if the particle is maintaining the polarization, that means its depolarization ratio is low and the particle is more spherical. Whereas if the particle is depolarizing the light, that means the particle is a kind of non-spherical particle with higher depolarization ratio. So what we can infer from this parameter is, it can tell you about particle shape, okay, whether it is a spherical particle or irregular particle. So we have different parameters: optical depth, single scattering albedo, asymmetry parameter, angstrom exponent, LiDAR ratio, depolarization ratio. Some, for example, optical depth is telling you about how thick or hazy the atmosphere is due to aerosols. Single scattering albedo is telling you whether the particles are absorbing nature or scattering nature. Asymmetry parameter is telling you whether the particles are scattering light in the forward direction or in the backward direction. Angstrom exponent is telling you whether the particles are small or large. LiDAR ratio is similar to single scattering albedo, but it is telling you the information at different sections of the atmosphere. The depolarization ratio tells you about the particle shape, whether the particles are spherical or non-spherical. So all such parameters we can derive using remote sensing as well as in situ measurements. So we have two options to measure all these parameters as I just listed. One is ground-based networks. You might have heard about AeroNet. You might have heard about MPLNet, EarlyNet, EarthyNet. AeroNet is ground-based networks or network of measuring the aerosol properties, basically optical and physical properties all across the globe. This figure tells you the location of all these stations. MPLNet is for micropulse LiDAR network. EarlyNet is in the Europe. EarthyNet is in the Indian region. So we have such ground-based networks which can give us very accurate measurements of different aerosol properties. But the problem here is that these are all sparse. You cannot cover the entire spatial domain. And let me also tell you about one of the most common instrument which is being used and which we are also using in most of the field measurements. That's the sun photometer. Here the basic fundamental is that the light comes from the sun. It is getting collected by the collimator and then it is passed to different wavelength channels, and there it is detected on photo detectors, and then we analyze the signals and aerosol optical depth can be obtained. Similar, if you go further with different wavelength regions, you can also find out angstrom exponent, etc. So just to brief you about what are the typical instruments in these networks. There can be other a set of systems also. For example, there can be micropulse lidars, there can be my lidars, etc. So we are not going into detail because this session is more focused towards remote sensing and mainly on the satellite based remote sensing. So, we have, what solution we have if we need to cover the entire globe? Okay, if we need to have a continuous spatial observation, satellite based measurements are the solution. The key takeaway is the ground based networks are highly accurate, but these are point based. You cannot cover the entire space. The satellite based observations are continuous in space, but then there are uncertainties associated with the measurements or the retrievals. We will talk about it in detail. So, there are different kinds of remote sensing sensors on the satellite systems. So, one broad classification is passive sensing and active sensing. In the passive sensors, the light is recorded from the surface, which could be either in the form of reflected signals or the emitted signals coming from the surface. And you have the top of atmosphere signal received in the sensor on board. So this is passive remote sensing. Whereas if on the sensor you also carry a source of illumination, for example, lidars. So if you have a lidar which can shine some streaks of lights on, or pulses of light on the surface and get back the backscattered light, this is called active sensor. So the difference here is, in this kind of sensing, passive sensing, you do not have any source to control the illumination. Whatever illumination is received from the sun in the form of short wave or the emitted radiations, that only are available for you to decipher. Whereas in active remote sensing, you have a control over the source of illumination. So you can have day and night operations, you can have controlled illumination, etc. As well as it also enables you to have the vertical profile of the atmosphere. So the major names here, as you must be aware of, on the Terra and Aqua platform, MODIS, VIIRS, then MISR, then AVHRR, then INSAT 3D, 3DR, then OCM, OceanSat, color monitor, OceanSat, ocean color monitor. So these are all major satellite passive remote sensors. And in the active category, we have Calliope on the satellite Calypso, which has been decommissioned in 2023, but it has given us more than a decade data that can be still analyzed if you need to understand the how the dynamics of aerosol worked over those years when the data was available. Now we have PACE mission, which can also give you the vertical aerosol vertical layer heights, etc. So these are some of the major satellite sensors. The important point here is, in the passive remote sensing, generally we get the columnar variability, and the resolution of the aerosol products may vary from one sensor to the another sensor, but you don't get vertical profiling. But in the active remote sensing, you have sparse sampling. This is also associated with low signal to noise ratios as of now, but you can get columnar as well as vertical profiling of the atmosphere. Right, so now let us try to understand what are the factors which control these aerosol properties, or which we can tap the information from to get the aerosol retrieved. Right, so let us look at this very famous diagram. On the x-axis you have wavelength, and on the y-axis you have particle radius. So if you see here, the range of wavelength goes something like UV to visible to near infrared, then this entire region is thermal infrared, and this is your microwave region. And here if you see, the particle radius is spanning from nanometer scale, which is typically for air molecules, then to Atkin nuclei, then dust, smoke, and haze. It's micrometer size. Like you have heard in the first or second session also, PM 2.5, PM 10, etc. So this going further are the sizes typical to the cloud droplets, then drizzle, and this is raindrops and hail particle sizes. So if you see here, the aerosols are falling in this category, right? And this category, if you see here in this domain, this in the wavelength region of thermal and microwave, these are behaving as Rayleigh scatterers. But in the ultraviolet, visible, and near infrared region, this is falling into the Mie scattering category. I hope you have an idea about the different kinds of scattering mechanisms. If not, I'll just give a small overview of that. So Rayleigh scattering is by the scatterers which are of the size very, very small compared to the wavelength which they are interacting with. Okay, so and the scattering is symmetrical in the forward and the backward, both directions. Most of the air molecules in the visible region behave as Rayleigh scatterers. Then comes Mie scattering, where the particle size becomes comparable to the size of the wavelength with which they are interacting. Here, forward scattering is mostly being dominated, but that is a difficult way to design the phase functions for different kinds of aerosols, right? So aerosols fall in this category of Mie scattering. Okay, and you can see in this picture, this is shown by ultraviolet, visible, and near infrared region, and this is the thermal radiation region. So you can see that in the ultraviolet, visible, and near infrared region, aerosols generally behave as Mie scatterers, whereas these and then change their property to Rayleigh scattering when you go to the thermal radiation domain. And here in the visible and ultraviolet region, the amount of scattering by aerosols is much higher compared to that when it goes in the thermal radiation regime. So in the last session, but one session, there was a question that was asking about the retrieval of aerosols compared to the atmospheric gases. One of the major thing that you need to understand is that the gases are majorly retrieved by their absorptive properties. So you generally, suppose you want to retrieve water vapor in this wavelength region, then you need to have dip region, a peak region, and then you can map the shoulder to the dip ratios and you can find out how much is the amount of a particular gas. But for aerosols, we need to see that they are behaving as Mie scatterers, and we need to model their scattering mechanism. So what are the major signatures of aerosols? Okay, so first let us see the wavelength signatures. If you see these three curves, this I have shown for dust, polluted dust, and pollution. It has been taken from Mishra et al. 2015. On the y-axis, you have aerosol optical depth divided by normalized with respect to the aerosol optical depth of 550 nanometers. The second graph is using the single scattering albedo, which we just discussed, and the third is for the asymmetry parameter. So if you see, this range is spanning from ultraviolet to visible to infrared, and then near infrared, and then thermal infrared region as well. So what you can see here is, if you are focused in this wavelength region, in the visible wavelength region or ultraviolet wavelength region, this first graph is able to separate the three classes of aerosols very well. The second also does so, but G is not showing that much changes. So G may not be a very suitable parameter if you are focused in this region only. But if you go further, then maybe a combination of different parameters can be workable for you. Further zooming in into the 440 to 870 nanometer range, here it has been taken from gsfc.nasa.gov, where four different types of aerosols are being shown. And you can see here that this sea spray and suburban are behaving similar when it comes to AOD. So it's very difficult to just tell based on the aerosol optical depth behavior across the wavelength that whether it is sea spray or suburban in this scenario. And similar here for smoke and mineral dust, again you have a crossover here. But if you cross this crossover point, here they are well separated, even here they are well separated. So the choice of wavelength will also determine how nicely you are able to separate different aerosol types. Similarly, another graph for SSA. So if you are here, somewhere here in this wavelength region, all three types of aerosols are having similar behavior. So it's very difficult to use this wavelength and distinguish between these three different types of aerosols. Instead, you need to go for take the help of other wavelength regions also. So next, coming to polarization signatures. This on the x-axis you can see we have particle depolarization ratio, which we just discussed in the previous slides, where if the ratio is high, that means the particle is more irregular, non-spherical. If the particle depolarization ratio is smaller, that means it's not changing the polarization, it is preserving the polarization, and the particle is more spherical in nature. On the y-axis you can see the LiDAR ratio. Again, LiDAR ratio was discussed. It tells you about the scattering and the absorption properties. Higher the LiDAR ratio, more absorbing the particle is, and vice versa. So if I have plotted here, it's taken from Illingworth et al. 2015. You can see that they have plotted different kinds of aerosols in this graph: smoke, pollution, aged boreal biomass burning, marine, dust and smoke, dusty mixtures, dust and volcanic ash. One thing you can see very clearly, this volcanic ash is coming out very nicely, standing out very nicely, because these are more non-spherical and associated with moderate LiDAR ratios. Okay, if you look at pollution, they are also having similar range of LiDAR ratios. Sorry, this aged boreal biomass burning, these are also having similar range of LiDAR ratios, but they are more spherical, so these are separated very nicely. Then if you see the smoke, this large area is being covered here because they are ranging from scattering to absorbing. Their absorption properties are varying, but they are more spherical, so they are concentrated towards the smaller particle depolarization ratio. Similar, marine you can easily separate because they are more spherical and more scattering. Dust and smoke, here it's a mixture here. So if you see the mixture of dust and smoke, this is taking up space where they are moderately non-spherical and absorbing. So you see here the LiDAR ratio range has totally changed if you go from dust to smoke, dust and smoke mixture, right? So the point here is, at a particular location, it is possible that there is a mixture of different aerosols present, and that mixture may have a different property compared to the individual type of aerosols. And polarization signatures can help you to distinguish between these different types of aerosols depending upon their sphericity and their scattering and absorbing properties. So polarization, if you are designing a remote sensing system, if it is also able to capture the polarization properties, this will additionally add to the information on scattering, absorption, and the shape of the particles. Then comes the role of scattering angle or viewing geometry. So we had talked about asymmetry parameter. The similar thing, it's manifested in the form of phase function. So on the x-axis you have scattering angle. Scattering angle is the angle between the scattered light and the incident light. And on the y-axis you have a phase function. So corresponding to different types of aerosols, the phase function changes. How do you decipher this graph? For dust, if you see, this is the black curve. If your scattering angle is changing from 0 to around 100 or 120 degree, your phase function is falling. That means lesser and lesser amount of probability for that kind of scattering. So that means dust is more scattering in the forward direction, right? So small angle scattering, right? And if you see this suit, the phase function change is not much compared to that of dust, right? So it is sufficiently scattering at different scattering angles. Another thing which is shown here is the viewing angle. So if you have a viewing angle at this location, this dotted line, you can see that this suit is very nicely separated from the rest, right? If you have a viewing angle corresponding to this here, then you can see that there is a distinguishability from black to red to green, right? So that means if you can change your viewing angles, that means if you have multiple viewing angles mounted on your system, that means if you have sensors looking at different angles, they can also tell you about different types of aerosols, because different types of aerosols will be scattering differently at different angles which you can view, right? So here comes the idea of multiple viewing remote sensing systems. then then there can be multiple combinations. For example, I've put here the role of scattering angle plus polarization. So if you have only the scattering angle information, this is shown in the first graphs. One is using the fine mode particles, the second is for the coarse mode particles. So you can see that mostly they are getting separated at certain scattering angles, and they are converging also at some other angles. So you can choose what kind of scattering angles you can have. But for coarse mode, the information is not very discrete. They are overlapping for most of the scattering angles. But if you further add the information of polarization, here you can see that you can take a combination of scattering angle and polarization to distinguish between different types of aerosols. So such multiple combinations, that means you can have multiple viewing angles, and you can have a system that can record the change in the polarization. So that can help you distinguish different types of aerosols in a better way. So on and on, there are different parameters that can help you retrieve the aerosol properties very well. For example, wavelength helps you to separate the surface from the aerosol component. It can help you to discriminate between the size, the type of aerosols. Phase functions can help you to understand the aerosol types. Single scattering albedo can help you to know about the scattering and absorbing properties. Asymmetry can help you about the forward and backward scattering behavior, and polarization can further help you to tell you about the size and the shape of the particles. Now, a very important question which is usually asked is, can we see aerosols from space? So I have put here a picture. You can see here the haze is visible over, this is the Ganges and the Bay of Bengal. You can easily see the haze which is separated from the surface. So before I delve into how do we retrieve these aerosols from space or from satellites, let us just have a poem here by Su et al. So they have published it something like this: first the sun and then the earth. Earth was dark, so there is no sky, so earth is dark. Satellites saw none. Then came sky and air, so that means gases. So satellites saw Rayleigh. So you see Rayleigh scattering, you see blue skies and all. Then came dark aerosol. So those aerosols which are absorbing. So if you introduce that absorbing particles in the sky, the amount of scattering will be reduced. So Rayleigh went away. Then came bright aerosol. Those aerosols which are more scattering. So satellites saw more reflections coming from the earth. Rayleigh grew a beard. Then came the brightest snowball earth. So you have snow covered mountains. Satellites saw only it because they are very reflecting, right? And then darkened only by soot and UV sand. So if you have highly absorbing particles sitting on the snow, so this will be the reduction in the signal. So this is somehow giving you a clue how do we retrieve the aerosols from space. So these are the major components which are going to add sensor signal. Add sensor signal means you have a satellite sensor. What it is going to record? It is going to record multiple things. Signals coming from the surface itself, signals coming from the portion of the atmosphere which the light is passing through. Essentially, it means aerosols, clouds, as well as gases. So, if I want to retrieve aerosols, that means I should be able to correctly retrieve surface reflectance, clouds, and gases. Right. So, if we how well we can account for the other three effects will determine how much accurately I can do the aerosol retrieval. So this is a general physics-based aerosol retrieval process. You have top of atmosphere reflectance, which is recorded on the signal. This is nothing but the total signal on this satellite. You will screen out the cloud and snow pixels because they are highly reflecting. It's difficult to retrieve the aerosols over these. So you screen them out. For the rest of the pixels, you do an estimation of atmospheric gases. So for that, we need to have those channels where there were dips in the transmission of the atmosphere signals. So if you have those wavelength channels, you can correct for the atmospheric gases. Then you need to do the corrections for the surface. So here comes the major trick, which different satellite sensors do different algorithms here. And once you have estimated the gaseous component and the surface components, then they use lookup tables which are computed using radiative transfer models, and then they try to fit the simulated top of atmosphere signals with the observations. Basically, they try to reconstruct the signal using the atmospheric gas contribution, surface contribution, and the aerosol contribution, and they try to simulate the top of atmosphere signals. They keep on varying the aerosol quantity, and when the top of atmospheric signal becomes same as that of the input signal which you have received, that time the aerosol is said to be retrieved. So it's an iterative process which people mainly use. So the challenge is the surface reflectance retrieval. Everything else is solved easily, but the challenge comes in the surface reflectance retrievals. Over the oceanic surfaces, it is easier because surface reflectance contribution over the water bodies are negligible in the visible region. So you can easily retrieve the aerosol component over the oceanic surfaces. But retrieval over land is very difficult because surface reflectance is also contributing majorly towards the signal. So how to solve that problem? So let us see the major aerosol retrieval algorithms which are used by different satellites. For example, MODIS uses different approaches. One is dark target approach. In this, the retrieval is done over the dark targets. Dark targets means those targets which are contributing very small surface reflectance so that the aerosols are visible. For example, you can see here in this region, if you see the dust over the oceanic region, this is easily retrieved, but dust over the land region is not retrieved very easily, right? In even worse is the situation in the mid IR region where you are not able to see any difference between the dust and the surface. So we are only retrieving for the darker regions. Similarly, here if you see over the vegetated surfaces, this is retrieved. Now what we see is in the blue and the red region, the dense dark vegetation are very are contributing negligible towards surface reflectance, so it's easier to retrieve aerosols over the dark targets. So this is your dark target approach. Then comes the deep blue approach, where we try to retrieve the aerosols over bright surfaces. So what do we do is, the bright surfaces are mainly the snow laden mountains or the hilly terrains, and the desert sand, which are highly reflecting. So because snow and cloud we generally discard, but for desert regions which are occupy a major component in the entire globe, so what we do is, we take the help of deep blue channels 412 nanometers here in this algorithm, and we also take the help of the information about the surface reflectance of these bright targets in different channels. And what happens is, the dust becomes dark in 412 nanometers. For example, here if you see in this region, here this is the entire desert region, but it becomes dark here. So whatever bright signal is coming, it is coming due to the aerosols, whereas it is difficult to derive this information in the 670 nanometer band, because now the surface and the dust component are equally discernible here, right? So the basic idea is, choose that wavelength region in which even the bright surfaces become dark. So this is another very widely popularly used algorithm, which is being used in CVIS, which is also being used in VIIRS, etc. And then comes another popular range of retrieval algorithm that is used by MISR, which is using the multi-angle, multi-wavelength approach. So here there are 4 spectral bands: blue, green, red and infrared, but there are 9 viewing angles. So 9 sensors with 4 spectral channels makes the information coming from different viewing angles, which we have seen in the role of the scattering angles that play, because in different viewing angles different signatures will come for different types of aerosols. So with this approach, not only are able to get the optical depth of the aerosols, you can get information on the size of the aerosols, you can get information on the type of the aerosols, you can also get the information about the height of the particular let's say smoke plumes, because you are slicing you are giving the information in different viewing channels. Then comes single channel approach, which has been adopted in INSAT 3D and 3DR, our Indian satellite. Here is a single channel approach. What we do is, here we take the previous 30 days radiance images, we convert this radiance to reflectance, and then we search for the clear composite image. Whichever is the clearest composite image, we take the monthly background of that particular date from MODIS, and we find out what is the surface reflectance. So for all those 30 days, we got a date at which we know the surface reflectance. Surface reflectance will remain the same over a period of 30 days or roughly. So we have the surface reflectance component, and now the same algorithm will work where you use the lookup tables and you retrieve the aerosol optical depth. So not only multiple channels can give you the total aerosol loading, but even a single channel approach can help you estimate the aerosol optical depth. Then another class of algorithms comes from the vertical profiling approach. Here, this is an example from Calypso satellite. So what happens is, we fire a laser pulse. That pulse travels through the atmosphere, and then in the layer of that atmosphere, the particles are scattering and absorbing light, and light is getting extinct at different sections of the atmosphere. This is being recorded, and this is also being recorded in two different channels with parallel and perpendicular polarization. So we take the help of wavelength, we take the help of lidar, we take the help of polarization also. So ultimately we are able to separate clouds and lidar aerosols. We are able to tell the types of aerosols, we are able to tell their loading at different levels, we are able to tell the types of clouds also, right? So this is a very useful way of knowing about what is there at different sections of the atmosphere. So let us see some case studies on what we can derive from these satellites. So one study I've put here is for a global scale. We here try to spatially correlate MODIS and MISR aerosol optical depth, and we could see that the correlations are generally higher over the densely populated regions as well as the associated oceanic regions. Then we also saw the annual variations, which is also matching. This gap is because we used at that time, it was using the dark target approach, and this is showing the annual trends of aerosol optical depth. Wherever it is this green, this parrot green, it is significantly decreasing, and wherever it is red, it is significantly increasing. So it was for a different decade, I think the last 10 years, and you can see that this aerosol optical depth is quite decreasing, except over, let's say, this region, over Indian region or over Australian region or the surrounding oceanic waters. And some similar information is also coming from the other satellite data. Then we also try to understand the different the distribution of different types of aerosols. So this first one is the total aerosol optical depth distribution using calypso. The second is due to the dust only, the third is due to polluted dust, and the last one is for the smoke. So you see here, this is the region which is mainly polluted, and dust is mainly concentrated here. Polluted dust, you can see very interestingly over Indian region. This is high over the entire Indian region. This is a mixture of dust and smoke. And then this is for the smoke only. Then we could also, using such studies, what I'm trying to show is what kind of research you can do. So it is a vertical profile section for different regions. Let's say this is for Indian region. This black line is showing the total aerosol loading at different sections of the atmosphere, and which is very, very high, close to the surface, which we are actually at our nose level, which we are breathing, compared to, let's say, if this is not this is, I think, okay, let me take let's say Amazonia. It is having a peak, right? But it's stopping here, but here on the Indian region, you can see it's going on and on, right? So what we are inhaling at just our close to the surface is very, very high. And then you can see the different levels of different types of aerosols. This dust here, and polluted dust is a mixture of dust and smoke. So polluted dust is what is being dominated over the Indian region, and it's falling very steeply. So again, it is concentrated close to the ground. And then this is for the smoke only smoke. So most of the regions are having a mixture of dust as well as smoke. So this is something to be taken care of. Then what else you can do is you can have an idea about how globally in different latitudinal and longitudinal belts across the vertical column the distribution is getting affected. You can see even here, important point here is on the smoke side, you will see that the vertical distribution shows lower values at just close to the ground, because smoke, being the lighter particles, tend to be stabilized at the higher layers of the atmosphere, right? Whereas The same is not true for polluted dust and dust. Then such kinds of trend analysis you can do, and what is really worrying is, over even if the total column trends over land and ocean and global trends are decreasing for those that particular decade, the picture may be changed by now. For smoke we were receiving a positive trends, right? So then such trend analysis can be done at different levels of the atmosphere. This is an example for the first 0 to 1 kilometer height of the atmosphere. So such kind of studies also can be done. Then even going further to the regional scale, this was a study done for a data void region, which is over the central Himalayan region, and we could study the vertical distribution trends in different seasons. We could see that there were very significant trends in the increasing trends in the lower part of the atmosphere, especially in the post monsoon season. Even throughout the length of the atmospheric column up to 9 kilometers, we could see increasing significant trends. The dots here are showing the significantly increasing trends, whereas these trends were found to be decreasing in the monsoon and the post monsoon region, especially in the upper layers of the atmosphere, but in the lower layers again we could see an increase. So lower layers are actually what we are inhaling. So on and all, this is a general aerosol retrieval process. The problem comes in the surface corrections or the lookup tables, which are huge. Either you do online radiative transfer simulations or you try to create the lookup tables, which the approach is generally the lookup tables, which is adopted by several satellites operational products. But if at your end, suppose you have a satellite data and you want to retrieve the aerosols, so what are the challenges in front of you? First, you need to see that you have some channels which can account for the atmospheric gases correction. If so, you do that. Then you need to have some algorithm which can retrieve the surface reflectance. You also need to have some kind of radiative transfer. Okay, so that could get the simulation of top of atmospheric signals. So at IIRS, what we try to develop is an IAOD software which uses a simplified physics based approach. So we did not use any lookup tables. We approximated the surface reflectance. So we had simpler equations, and this model was generalized model which we could apply on different satellite data sets. This is an example for Landsat, Sentinel-2, LIS-3, AWIFS. So a generalized algorithm was created. What we needed to know is, you need to know the top of atmospheric signal coming from different bands. You need to have the angle files, right? These are the two things that you need to know. Then comes in the surface reflectance retrieval. We assume that there is no aerosol impact at the first approximation, and then we do the iterations, and we try to estimate the asymmetry parameter, single scattering albedo, and ultimately the aerosol optical depth from the data itself. So we try to validate the results with AeroNet. We could get a fairly high correlation between AeroNet and the retrieved AOD for all the sensors which I just listed. And spectrally also we tried to check for different spectral bands. It was coming fine. Then it was also compared with MODIS for different surface and types of surfaces. It was comparing well. Then visually also you can see this is these A and B the zoomed in regions for Landsat, Sentinel, and MODIS. Again, for different kinds of sensors, they were visually also matching well. And then this is view of the IAOD software. We will give you a brief overview of this software in the last session on hands-on, so that you get an idea how it works. Similar, you can also go for such an approach. We could get an IPR copyright and some publications on this approach only. And also we, as I mentioned you about deep blue algorithm, we also try to implement the deep blue algorithm over OCM2 OceanSat data. And now this was an overview regarding the the physics based retrievals. Now comes, I'll just brief you about the machine learning based retrievals, because today, in every sphere, in every applications, we are seeing the use of AI ML, and AOD is not an exception, or aerosol retrieval is not an exception. So, what is the basic approach which we adopt is, you have some predictor variables, you have some influencing factors, you apply a model, and then you interpret what could be the feature importance of different parameters, and how you are going to relate the estimated aerosol parameter with respect to the actual parameter. Regarding the source apportionment, I think in the next lecture we will have a detailed overview of that by Dr. Ojha. So I'll not go into that detail. I'll just tell you about, let's say we have tried to perform some PM 2.5 estimation, air quality AQI index estimation. So what we took is, we took satellite aerosol optical depth, we took CPCB data, we took several meteorological parameters, we took land surface variables like NDVI and atmospheric parameters. And let's say if we want to particularly focus on wildfires, we also took in the amount of burnt area, etc. So such kind of input predictor variables go inside, and then you have a model, machine learning AI ML model, and then you get the output predicted, right? Similar work is going on for the classification of aerosol types, where we first retrieve the aerosol properties, and then using that information, some clustering or classification supervised or deep learning based approaches. Even we are trying to check with the quantum based machine learning approaches to estimate different types of aerosols. So such work is on at different centers across the globe, how well we can retrieve the aerosol properties using AIML. So there are limitations, there are challenges with both physics-based retrieval and machine learning-based retrieval. Where physics-based retrieval requires accurate radiative transfer models, several assumptions, and it is also sensitive to the instrument calibration errors, noises, a good SNR is required, cloud contamination and surface reflectance uncertainties further add to the problem. And if you have multiple channels, multiple angles, polarization information, then it becomes heavily computationally intensive. Machine learning based aerosol retrieval requires the large amount of, first it for, because large amount of data goes into the training, so it requires high quality training data set. But then there is a risk of overfitting, leading to poor generalization. Sometimes it just acts as a black box, so physical interpretation becomes difficult, but with the add on to the explainable machine learning, this thing is getting eased off. Then if there are biases in the training data, if your data is limited to a particular geographical domain or in a particular season, it may not be generalized to different geographical domain or season or the time of the year. So the solution is, we should have a hybrid approach, we should have a physics driven machine learning approach that can help solve the problem more efficiently. So with this, I stop here, and I'll be happy to receive the questions. For that, we'll have a 2-3 minutes break and we'll be back. Yeah, thank you. Okay, so welcome back. I have a few questions which are listing here. So one question is, can the size and type of aerosols be different at different months and season of the year at a city? Is plantation really an effective method to stop pollution due to aerosols? Okay, yes, it is highly variable. The type of aerosols, the composition of aerosols, and the size of aerosols are a function of the time of the year, as well as the geographical domain where you are located, because it is because the aerosols might be created locally, and that local creation may be season dependent. For example, if it is a parali burning, which is in news everywhere, so that is season dependent, that will happen in the post monsoon season. And if it is dust, it will be more dominant in the pre monsoon season. So the source itself changes. Second could be they could be getting transported from one place to the other. So that is also dependent on geography, on the season, because in different seasons you have different meteorological parameters, different wind directions, different wind speeds. So that will vary, yes. Second, somebody said plantation really an effective method to stop pollution. Stop pollution will not say, but essentially, if you have more greenery, if the greenery increases, we have seen that there are studies which could show that there could be a reduction in the aerosol loading, primarily because the aerosols will get physically also an area to get settled to. Then they further travel into the pores of the plants, leaves, and all, and then they can be decomposed into different forms. So, yes, it will help reduce if we go for more greening. Then Ayush is asking, does the AQI depends on the very much depends on the aerosol, and exactly how it is dependent? Okay, AQI is air quality index. It is governed by what are different parameters in the atmosphere. It could be due to PM particulate matter 2.5, 1, 10, or it could be due to sulfates, nitrates, then sulfur dioxide, then different kinds of pollutants. They can make up a total AQI of an area. So aerosols are effectively a large component of that, but uh, um, not the only component. Okay, the other gases, etc., will also contribute in different forms to the air quality index. Then another question is, why do aerosol physical and optical properties change even when their chemical composition remains constant? So, because the difference in their size, shape, or morphology, mixing state, or the presence of hygroscopicity of the water, that means the presence of aerosol water component in the aerosols, all this will determine particle mass. Acha, okay, so because scattering is an optical interaction, okay, and it is tied to the physical dimensions of the particle and its shape, its form, and relative to the wavelength with which it is interacting, rather than its bulk mass, right? So mass is coming out as a consequence of the size and the composition, but it does not directly govern how this scattering will happen, depending on which wavelength is there. Then, why absorbing aerosols exhibit a stronger signature? Where is it? In UV wavelengths compared to visible. Yeah, that's the property of that particular type of aerosols. So that's why we call it signature. What we can do is to tap that signature and to assess how much is the amount of absorption, or how much is the amount of absorbing type of aerosols. We can take the help of those UV wavelengths if they are there. Then, why does improving aerosol remote sensing remain more difficult than cloud remote sensing despite? Okay, because first, aerosols are very tiny. Okay, they are well dispersed, they are very dynamic. Okay, they are very heterogeneous, and their signals, the signals coming from aerosols, are also in competition with the signals coming from the surfaces, right? So it's definitely a difficult regime to deal with. Which open source software good for image enhancement? Okay, we are not particularly dealing here with image enhancement, but you can opt for QGIS. Then why are thermal infrared observations ineffective for many fine mode aerosols? Why can high aerosol concentration still produce low satellite detectability? As I said earlier, that um, the behavior of aerosols is more as the form of mice scatterers in the shortwave region, whereas in thermal remote sensing, their effect is mostly in the form of Rayleigh scatterers, right? So we are it's difficult to see their prominent effect in the thermal IR region compared to the shorter wavelength regions. And even if there is a high aerosol concentration, that aerosol concentration itself is not sufficient to detect the aerosols. The type of aerosols, whether it is scattering or it is absorbing or it is a mixture, on which type of surface it is present, if a bright aerosol is present over the bright target, or if a bright aerosol is present over a dark target, both detection capabilities will be different. If a dark aerosol is present over a dark target and dark is available over the bright target, again there will be a difference in the amount of uncertainties that we can get through. Okay, so can aerosols produced by biomass burning increase fertility in the soil where it gets deposited? So uh, it depends on what kind of aerosols are being produced by biomass burning. How will the accumulation of soot in the soil will increase its fertility? So that's the question. Okay, so far I have received these many questions. I think now it's the time. I am taking the time of the next speaker. So be tuned with us. In 2 minutes, we'll be back with the next session. Thank you. वीडियो वीडियो नहीं है. Yeah, welcome back to the fourth session in today's workshop. So I'm pleased to introduce Dr. Narendra Ojha from Space and Atmospheric Science Division at Physical Research Laboratory, Ahmedabad. Dr. Ojha's research focuses on atmospheric trace gases and aerosols, meteorology and dynamics, and advanced atmospheric modeling, including applications of AIML to environmental systems. Dr. Ojha has a strong record of research and publications addressing the chemical and physical processes shaping Earth's atmosphere. Sir, we are grateful to you for agreeing to deliver a talk to our audience, and I welcome you to this workshop. Over to you, sir.
Thank you, Manu. Thank you very much for inviting me. And it is a great opportunity to talk to a diverse audience interested broadly in atmospheric science and more specifically climate. So, as it is clear from several important talks since the morning, that atmospheric processes are quite coupled and it is very difficult to study them in isolation. So aerosols and gases come also in that line. So it is a simple picture now. Of course, a detailed introduction was covered by Dr. Yogesh Kant in the morning and then Neeraj. It is kind of a summary. So to highlight how complex it is to do the modeling part, so you can see that all of us can see that emissions are from different form. Many are in form of gases, some are in form of particles, and then they undergo several different transformation, including through chemical, physical, and then they are transported from one place to another. For example, emissions from transport, they can get emissions from traffic, they can be transported to other places. Similarly, industrial plumes, they can go. Then sometimes we forget that natural emissions are also very important. So trees, they are emitting major precursors of ozone and aerosols, and these precursors are called VOC, volatile organic compounds. From agricultural activities also ammonia comes, which forms ammonium aerosol. Halogens are also emitted. Some aerosols come directly if you burn biomass, if you burn fossil fuel or coal. So some aerosols are directly emitted. But as I said, from NOx, SO2, ammonia, they can also undergo chemistry and physical changes and they become aerosol. So aerosol have very diverse sources and very diverse processes that control their distribution on the earth. So a major implication of aerosols, you all know, is health. So in this is a picture when there are a lot of aerosols. So you can see how much haze gets created, and our public health is hugely impacted by aerosols. But aerosols are not only important for health; they have a lot of role also in the climate. So it is very important to understand what is the source at a given location, what are their main sources for a given region, study region. So a lot of computational and observational and satellite based studies are being done. So why exactly one has to do computer based modeling? So first is, of course, we cannot do measurement every place, although we know that health effects we have to understand not only in urban environments but also in rural environments. Similarly, if we have to understand climate, we have also to study Himalaya, Tibetan Plateau, Indian Ocean. So we cannot have observations all the time, all places. So we need models so that we can have a graded map of the entire world, or maybe our study region, entire India, or entire Africa. But models use is not only to fill observational gaps. Their major objective is also process studies. What is the role of biomass burning? What is the effect of atmospheric transport? What is the role of fossil fuel burning? So understanding the sources are how much sulfur dioxide is getting converted to sulfate. So chemistry. So to understand different processes, to compute contribution from a given source. Then many times we feel questions, scientists, engineers, policymakers, they have a question like what if scenario. sometimes we see that suppose we turn off all the biomass burning in North India, what will happen to its air quality? How much aerosol will go down? Similarly, sometimes we think that if industrialization is suppose our fossil fuel burning becomes double, so how it will affect aerosols? So it's not that we will actually double the fossil fuel and then we will see, okay, it impacted earth in very bad way. So we will do some computer based simulations to make an assessment and to assist the uh, policymakers. This process that we understand atmospheric chemistry and dynamics and run a computer model and then inform somebody that how you have to make better policy. So this is called science informed policies. Then we sometimes we need that, okay, how will be air pollution tomorrow or after 10 days, or suppose when we try to achieve net zero, so how it will be, aerosol loading will be there. So these are called forecasting and future climate predictions. So as you can see that models have a very diverse applications. So there are a lot of many different objectives that can be addressed using high performance supercomputers and understanding atmospheric science. So where we put these things, because Manu talked a lot about looking earth from space, and Neeraj and Yogesh bhai talked about conducting different type of measurements and seeing earth from space. So there are so many different angles on from which we are trying to look at aerosols. So how, where fits the modeling? So there are different type of observations, and as I said earlier, from models we try to reproduce that type of patterns which we are seeing in the field, which we are seeing from satellite. So if we can compute similar pattern from a computer model, then that means we understand what is controlling the distribution. Then we can use model to answer all those questions that I discussed as the modeling objectives. So they all go in very good synchronization, that it's not that models are alternative to observations, or satellites can be alternative to model. So all these measurements, different type of measurements, modeling, satellites, they are basically developed together so that our understanding and application that can be more. So what is the main philosophy of modeling? So starting is knowing the physical, chemical, and other scientific principles. We have to first understand as much as the of the system we can understand. As I listed that what are the main sources. So we need to understand the emissions from fossil fuel, biomass burning, natural processes. Then we thought that, okay, chemistry is important. So we have to list down what all chemical reactions are possible in the conditions that are there in Earth's atmosphere. So understanding first the science and then transport. We, if aerosols are emitted at one place and winds are coming from west to east, so probably they will push this aerosols from west to east direction. So that is basically effect of dynamics. Similarly, role of boundary layer. Suppose there is a in a summer season when boundary layer is 2-3 kilometers, so the aerosol that will be emitted near our surface, it can be well mixed up to 2-3 kilometers. But on other day in the cold winter conditions, when boundary layer is not evolving, so then all aerosols will be trapped near or close to Earth's surface. So these all are physics, chemistry, and dynamics based scientific information. This we need to have in our hand to start building what we call a conceptual model, to conceptually talk about these things. But main catch for modeling is that uh, only knowing things conceptually, we cannot have a model. We need to convert these things into a mathematical formulation. We have to understand that, okay, what type of conditions should be there, how much emission comes from a given source. We have to convert these things more in quantitatively forms. If we are saying that chemistry is important, so we have to actually estimate the rates of chemical reaction. So that type of mathematical formulation is important. We have to solve, so that we can solve, we can calculate. And then once we set up this thing from conceptual to going mathematical form, then trying to run this type of codes, And most important is that you have to evaluate how is this model becoming. As I said, that if our model can reproduce the real world data, then that model is good model to answer questions related to the system. So evaluation is very important. Many times we understand process conceptually, but we make errors while doing mathematical formulations. We make some simplification, which is not good. We have to have more complex treatment. So if you simplify something which has to be treated in complex way, so it will reduce the performance of the model. So comparison of model outputs with experimental values, that is a very important point. For example, you see this snake and ladder game, many of you have played. So you cross all the steps, but at this point, if a model is not matching with the experiments, then it is a trouble. You cannot directly use the model output. So where you have to go, you may need to go really back in time. You have to see whether our formulation is not good enough, not detailed enough, or some important physical process is missing, some chemical reactions are missing, some natural biological sources of aerosols are missing. Why we are not getting a better agreement? And this is a continuous process. It's not that we have now a good model and this we can run for next 10 years. So climate models, weather, atmospheric chemistry models, they are in continuous development. So compared to previous years, at this moment we have better models, and compared to present models, we are expecting to have better models in the future because of this whole process. We will make new measurements, we will compare our models, we will learn new things, we will add them into the conceptual model, and this process will keep on going ahead. So models are of different scales. Sometimes it is necessary to simulate entire Earth, which is called a global model. But we cannot have very good resolution if we have to cover entire globe. Take like taking a picture of a very large group of people. So then we cannot easily focus on each and every one. But suppose some of our colleagues are in some place, so we can cut the other regions and we can zoom into that at a very high resolution. So they are called regional model. And as I said from the start, that these things are not very independent of each other. So if you have to run a specific part of the earth, you have to know what is on their boundaries. So someone has to also run the global model to provide this global modeling capabilities. Similarly, suppose you want to run a model starting today, so you should be knowing what was the initial value, because in atmosphere things are not 0 0, you are starting from somewhere. So again the global model output is coming into picture. So for different problems we can use different type of architecture and systems, but their developments and science, there is some overlap. So as was mentioned in the schedule, that WRF-Chem is a very popular regional scale model. Advantage, as I said, is you can use a very high resolution, you can conduct high resolution simulation for a particular study region. And but there is another very important advantage of regional model, that because you are running only one part of the earth, you can take options of physics and chemistry which suit better to your study region. But if you are running entire globe, most of the time you have to take a common setting which is not too good for suppose India, but which can also take care of Africa, North America, because you are running entire world. So you cannot choose a very suitable condition for your own region. You have to take something that is kind of average that can work everywhere, but it may not be very good for a given region. But in regional modeling, you have this choice. You are only running India or Africa, so you can take a physics scheme or take a aerosol process that is very suitable to your region. But as I said, global models are also continuously developed. For example, EMAC is developed from German groups. Geoschem is developed by US, especially University of Harvard. And many reanalysis data sets are developed. When a model is giving you some output, but you have some independent experimental value. Suppose your model is giving black carbon 20, but you are seeing in experimentally that it is 25. So you correct your 20 to 25. That is called kind of using experimental data to improve your model fields. So that process is called reanalysis. Of course, it is much more complex, but I am just trying to give you the philosophy behind this. And what all these models are doing, they divide the study region into different boxes. And for each box, they try to calculate concentration of a given aerosol or gas. They add all the emissions of that. They see what all chemical reactions can produce it. They subtract all the chemical losses, and they subtract the effect of deposition. Similarly, anything that is flowing because of winds from a different place to my place. Suppose I am in Delhi and some fire is happening in Punjab, so that can flow to the Delhi. Similarly, if I am in Punjab, so some fire is there, it can flow out of my domain. So that is your flux in and flux out. So if I know the rate of each process, so I can tell what will be changed in 1 hour. So I will sum basically all the sources. I will subtract all the things. So that's how. So this is how it is happening in the models. But in reanalysis, there is another advantage that if model is not matching with measurement, we can do some tweak, some kind of tuning using measurement data. A new approach in modeling is becoming very, very popular. That is called through AI ML based applications. That is artificial intelligence and machine learning. So initially, a very good advantage was that unlike this type of regional and global models, which you almost always need a big high performance computing system, AI/ML you can also run on very good laptops. So that is one advantage. That is how among students it is very popular. If you see, many students are running AI/ML based codes. So because it is possible to train a model on their laptops and do some simple simulations. So AI/ML, but of course this advantage is right now uh, slightly changing also. AI/ML machines are also needing very good computing resources. So another advantage that is still relevant is that AI/ML models, they can directly learn from your data. If you supply them measurement of from satellite, or you give them output coming from a machine, or you are taking some samples, you can directly see the output to a ML model. They are not depending much on the atmospheric science information. So they are more data driven models. So many times, because when we do modeling, as I said, we have to understand all the sources things. But of course, scientists do not know all the sources, all the things. There are, whichever we understand also, there are also uncertainties. And then there are some sources which we are not fully aware. So these models are sometimes missing many things. But AI/ML models, they are not knowing process wise. They are going based on data. So once they start seeing different parameters, so sometimes they can learn something more that in terms of data that we may not understand fully in terms of process. So again, these two type of modeling approaches, they are very complementary to each other. And I will show some simple examples to make more point. So how we are going to understand this type of models? So we have to go stepwise. So we have to identify each source. And when we are giving you this very simple equation, please note that each part that itself is sometime a large module, large set of computer programs. For example, if I have to just calculate emission, here you go. Emissions can be from anthropogenic sources. So these come from inventories. Inventories are basically kind of data that how much fossil fuel was burned in this area, how much traffic was there. So, and suppose 1 liter of fossil fuel is burned. So how much aerosol or gases or precursors it will emit. So those are basically raw data, inventory data. So they provide the anthropogenic emissions. Sometimes people also use satellites to estimate the emissions from a region. Similarly, biomass burning, that is another emission source. You see all the time wildfires in the forests or crop residue burnings. So their inventories are also utilized. Natural emissions, for example, trees also emit hydrocarbons. These hydrocarbons, can become aerosols. So we have to have a good understanding of the emissions coming from natural sources. And dust. So dust depends upon the what are the surface properties. If surface is erodible, so we have to understand the land use, land cover that we can see from satellites. And then not a surface will emit dust all the time. If it is erodible surface plus winds are strong, then they will inject the dust from earth's surface to the atmosphere. So as you can see, just we are taking one term of the equation, and that term itself is so much complicated, so much science and technology we have to use just to calculate one term. So similarly, we have to calculate what is the rate of deposition of different process, different aerosols species. We have also to calculate transport, for which we need to understand the winds. Winds we have to understand. We have to understand boundary layer dynamics. We have to understand convection. So it is not possible to understand each and every step used in the model, but to a broad summary that okay, these all are different parts of the model, and by putting them together, we can do a simulation. And this is a good question for all of you, that from here you can have a very good guess. You can think why models do not match with observations. This is very clear because there are so many different processes. So it is possible that there are uncertainties in each and every component. So when we sum up and do the calculation, it is possible that we may not match the what we see experimentally. And another point we should always remember is that there will always be some bias in the model output. So whenever we use the model output for assessing anything, we should always consider that how this model compares with the experimental values. So that gives us idea what are the uncertainties that we are going to have in our results, our scientific findings. See some applications. So when we are trying to see entire globe, you can see winter and summer condition for aerosols. So all of you now by now very well understand that PM 2.5 are the small particles, and they are most important for our public health. So you can see there is high aerosols simulated over entire Indo-Gangetic plain in part of East Asia. These regions, you know that they are regions of high anthropogenic activities. They are very densely populated regions. But you can see other regions also where there is high levels. See this, especially during May, dry summers. So there is the effects of deserts, desert dust. Similarly, in this region, Africa, there is also desert area, plus there is also biomass burning. So that type of smoke is flowing out. So if you know the emission inventories and you put overlap them with the wind dynamics boundary layer, so then you can see the distribution. That is what we are showing here. Lelyville et al. Used similar global model and tried to estimate health effects. So you can see that in India, in Asia, and parts of Africa, impact on human health is more because of aerosols. So this type of model fields, they are getting used for estimating the health impacts. Then to identify the sources, so you can focus on sulfate aerosols. You can see that when energy generation emissions are included, then these levels are high in these regions. But if you turn them off, so then air can be cleaner, sulfate level can be really, really low. Similarly, ammonium, you can see a lot of ammonium is flowing here. Organic carbon, black carbon, you can see, as I said, that forest fires, wildfires, they are injecting a lot of emissions of the black carbon. So this type of applications we can do from the models. We can understand their sources, we can understand their transport from one place to another, we can understand their health impacts. But if you look at different models, for example, this is CAMS model, reanalysis data from ECMWF, MERA2 is from NASA. Recently, they have developed another product called MERA2 CNN. They have basically used some measurements to calibrate this MERA2 using AI. And then this product is also very interesting. It is satellite derived. They are looking the total aerosol and trying to infer what will be the aerosol concentration at the Earth's surface. So you see, when we are having different retrievals and model simulations, that they are very different. For example, CAMS is giving you much more aerosol here. This is a desert region, you can see. So much more aerosol here. In Mera-2 it is less, Mera-2 CNN it is even less, and satellite derived. So you can see in winter also you can see the levels in CAM series analysis is much more than the satellite derived data. So there are many times difference from one model, one type of reanalysis to another. So we can use some regional scale models by including all the information from that region at high resolution. So compared to global models, we can use very systematically what may suit for a given condition. For example, we are showing some example of WRF-CAM model. So you can see this WRF-CAM, if you compare our model simulation with the IMD data, so you can see the temperature is comparing very well. Similarly, humidity you can see, humidity also comparing very well. Wind systems also. So our models that we are running at high resolution, they are trying to reproduce the actual observations made by India Meteorological Department. So what it means is that using this type of model, we can calculate the distribution and transport of aerosols. So this is the distribution of PM 2.5 calculated using this same model. Top row is showing ozone that we can ignore as of now. So this is the distribution of PM 2.5. But you can see from regional model, we are getting much more aerosols than there are values in the global scale models. So what this tells us that from different to different aerosol models, and because of differences in the atmospheric dynamics from one model to another, the aerosol distribution can be very different. So if 3-4 models, they give very different results. So how we go ahead? So we try to compare them with experimental value. So now we are comparing this regional model with experimental value. So this is a cruise track in the Arabian Sea, and you can see the model is kind of following the variability in the measurements. But we need more. So suppose this is a very important problem for which we try to apply this model. In each winter, all of us know that this Indo-Gangetic plain, it becomes a global hotspot of high aerosol loading. So there are many big cities like Delhi, Lucknow, Kanpur, Varanasi, Patna. So they all face a lot of high air pollution. So you can see that PM 2.5 that is measured by different instruments versus our model computations. So you can see there are some uncertainties, but they are still trying to reproduce this variability. So you can see clearly from October in northwest there is high aerosols, but during December the entire Gangetic plain is experiencing very high surface concentration of aerosols. So this is our model simulations. So what happens when we turn off the biomass burning? So you can see that best effect is coming in northwest, this Punjab Haryana region. But in November, December, most of India gets benefited if we can remove the emissions coming from the biomass burning. Interestingly, during December, when air pollution is very, very high in most of this region, then biomass burning effect is less than 10%, you can see. This all is plain blue color. Some fires are active, but they are in the Himalayan foothills region. They are not affecting the Gangetic plain. So this type of regional aerosol models, they help us to pinpoint what is affecting us and when. So if we have to advise some policies during October, November, it is very helpful if we can reduce the biomass burning in the northwest Gangetic plain. But if we have to focus in December air quality, then we have to focus on other sources like fossil fuel burning, traffic, industry. So that time fires are mostly affecting the Himalayan foothills. So suppose IIRS and other nearby places, if you have to see, so you will find some aerosols coming from this biomass burning. So this type of model simulations are very good for understanding the sources and dynamics. But they always need to have some comparison. So I'm showing comparison of organic carbon, elemental carbon, sulfate, nitrate. So we normally see that this is Mount Abu, Delhi, Ahmedabad, many regions, and left is basically model, right is from different experimental groups. So you can see that models are able to capture the aerosol chemistry, but they are typically telling us less sulfate. If you see green color, so you will see more green in measurement, less green in the model. So that means in models we are producing less sulfate. So probably sulfur has to be improved. Similarly, black carbon, if you see, that is red black carbon. That is orange color here, EC. So you can see model is more orange than the observations. So this is interesting because black carbon is a absorbing type aerosol. If visible light is incident on black carbon, because it is black, so it will, that is how it is called black. So it will absorb light, but sulfate is a scattering aerosol. So in the models, we have more black carbon, but less sulfate. So basically models aerosols, they are more absorbing than in the reality. So these type of features as a interested modelers, you people have to understand that if we use models, so we have to understand that their composition, if there are differences between the measurement and model, so probably we may not accurately understand the climate impact of aerosols. Similarly, we can look at the aerosol sources and their transport. So this is effect of biomass burning from India, you can see. But you can see the other parts of Indian Ocean when the effect is coming from the Southeast Asia. Natural processes are, we are finding that they are very poorly understood. Of course, natural emissions are a very major precursor of secondary organic aerosols. So this is our simulation of formaldehyde, that is a tracer for natural emissions. So this is data from NASA's OMI mission. So you can see in models we are finding much more biogenic process, but in which is similar to OMI, but some other satellites are showing less biogenic emissions. So probably we need more instruments to measure biogenic emission in different parts, because with global warming, these natural sources will be becoming more important. And how natural processes produce aerosols, this type of parameterizations are still not very good. This is a simple example of how aerosols are affecting the radiation. So when there are aerosols, you can see the short wave radiation that is reaching Earth's surface is reduced by 40-50 watt per meter square. Most of South Asia, radiation is reduced because of aerosols. So if radiation is less, so it is also slightly lower the boundary layer height. So what is happening that because of aerosols, boundary layer is coming down, it is giving a feedback to aerosol concentration. Because of shallow boundary layer, aerosols are additionally enhanced by suppose 3 to 5 or 7 microgram per meter cube. So this is what you can call it as a positive feedback of aerosols. So aerosols bring down the boundary layer, and because of that, aerosol concentration is even more increased. So probably this is a key player in the enhancing the air quality issues in Gangetic Plain. So this all are process-based modeling. If we add aerosols, they directly talk to radiation, and then all the feedbacks get active into the climate models. So now we will try to take a totally different approach that we call as a machine learning. So in machine learning, we don't start with the processes, we start with the data. So suppose we have temperature, boundary layer height, wind, precipitation, wind speed, this different type of data. I'm showing one case for Dehradun. So IIRS is in Dehradun, who is organizing this program. Similarly, another is Ahmedabad, that is where PRL, my institute, is located. So you can see some of the parameters like winds, they are very strongly correlated. So this is my PM 2.5. You can see that wind direction, humidity. So different parameters are very nicely correlated. So depending upon which parameters are more correlated with PM 2.5, suppose wind is correlated. And in machine learning, even a negative correlation is useful. Suppose PM is negatively correlated with temperature. So still it is a useful predictor for me. Sometimes we see that negative correlation is not good, but in machine learning, positive or negative, both correlations can help us to make better models. So we are trying to test many models. So compared to this global model reanalysis, our machine learning models can produce much lower errors. So this is for Dehradun, this is Ahmedabad. You can see that we can use machine learning to kind of calibrate the global model datasets and bring them close to the measurement. And similar to correlation analysis, you can analyze the feature importance of different inputs. So you can see that in controlling Dehradun's aerosol, temperature, boundary layer height, their humidity, they are playing major role. But in Ahmedabad, humidity is not most important. It is relatively less important. So that gives you some indications based on the data. So some of our group members, my students, they are trying to build an entire two-dimensional model based on the machine learning. And we are trying to see like Delhi, Kolkata, many stations. So our machine learning model based on deep learning, they are comparing with measurements in much better way. So I want to summarize it as that global and regional scale models, they are very helpful for computing aerosol distribution and their composition by taking into account the emissions, their chemical transformations, and uh, wind dynamics, boundary layer dynamics, etc. But these models still have a lot of uncertainty when we compare the PM2.5 mass and composition. From one model to other model also there are differences, and between a model versus experiment also there are differences. What it means is that the way we understand aerosols budget and their impact on public health or even on the climate, they may be very uncertain, especially in the regions where models have large uncertainty, such as developing South Asia or Asian regions. So probably there is a lot of work to be done by new students who are attending this type of programs. They can really contribute and make things better. One approach that is becoming popular is AIML, because if you don't understand the process fully, but you have experimental data, you can still come up with a good model. So that is a different type of approach. And some of us are using the experimental data, AIML, and the model output from conventional models, trying to calibrate them and improve them. So these are some major future directions. Of course, it is very difficult to talk in 40 minutes and provide a very detailed understanding on aerosol modeling, which is really, really complex. And even people who are doing aerosol modeling for many years, they still have a lot of questions and a lot of discussions. So it is a very simple overview. So for further details, you can anytime write to my ID, Ojha, that is my surname, and ESM calls Earth System Modeling @gmail.com. And you can also write to my official ID. You can get it on our institute's website. So this will need much more discussion than what I could compile here. So thank you very much.
Full engaging and informative talk.
Thank you.
Yeah, thank you so much. And we'd like to have some questions from the students. Maybe we'll meet again in 2 minutes. We can break here for 2 minutes. For that, I can
Sure.
compile the questions from different platforms. And I'll come back.
Sure.
Yeah. Okay, so I have few questions with me, Dr. Oj. The first one is, can you hear me?
Yes.
Yeah. So the first question is by Vipul. Why is it difficult to represent aerosol mixing state accurately in global climate models?
Right. So yeah, so because this mixing state is continuously changing, and depending upon uh, how distant you are going from a given source, and our resolutions of models are not that high. So it is a combination of complex chemistry and a plus saving of computations. So probably for some locations, in some way, we can calculate the aerosol mixing state better. But in the global models, when we have to cover entire globe, so some details we compromise to save computational power. And it is not specifically for aerosol composition part. Also, gas phase chemistry that is very simplified in global climate models for the similar regions. And another reason is that very detailed aerosol composition data is often not available. How it is changing when you are going away from the source. So that are few important factors.
Yeah. Okay. So another question is, why is long-term trend comparison between satellite aerosol records and model simulations particularly challenging?
Yes. So yeah, so because as we see that the models, they need the accurate emission inventories, and some regions where we have very good records of anthropogenic emission changes, so their models have been better capturing the emission trends. But some other regions which are rapidly developing, where emissions are changing in a competitive way. For example, some processes, their emissions are increasing, anthropogenic emissions are generally increasing, but because of some new regulations and uh, changing to renewable energy, we are also cutting down sulfur emissions. So when competing effects are happening, so we need to have very accurate information on the emission inventory. If we don't have accurate emission trends, it is difficult to tune the models.
Yeah. Yeah. So another question is, how reliable are the aerosol models to support air quality management and policy decisions?
Right, that is very good question. So as I highlighted myself, so there are significant differences between measurement and models. But when it comes to air quality, you can see the broad pictures that we are seeing in the observation, like high wintertime aerosol loading. Similarly, in Western India, you are seeing effect of dust, etc. So broadly, major processes are well understood and they are well captured by the models. Similarly, effects of biomass burning coming from northwest. So those are very properly set, because we have also good satellite data of fire counts. So that is going into these models. So similarly, there are several aspects of air quality management that these models are giving very good insights.
Yeah. So another question is, how does increasing the spatial and temporal resolution affect the simulation accuracy and computational cost? So if you can comment
Right.
on that.
Right. So increasing spatial resolution is very important, because if regions have complex topography, so for example, Dehradun and nearby Himalayan foothills, so even 10, 12-kilometer resolution is sometimes not resolving the topography properly. So Himalaya and other regions, they need high resolution simulation. Other reason is that emissions change very fast from one place to another. So normally today emission inventories are at resolution of 10, 12 kilometers. So I don't think that we can increase the resolution to very high, because then model will simply interpolate if we don't tell what is beyond 10 kilometer. Either we also have inputs also for 5-kilometer resolution, 3-kilometer resolution. Since we don't have those type of inputs, only topography satellites are giving us better data. So topography and related dynamics we can improve, but chemistry, emissions, we don't have better emission inventory at high resolution. So it may not be very helpful to run model at 5 or 2 kilometers.
Yeah. So one last question we can take, Dr. Roja. How do meteorological inputs influence the vertical distribution in chemical transport models?
Yes, so meteorological influence control basically the boundary layer dynamics convection. So in fact, most of models in Indian case, the not getting right amount of convection is a very important challenge. So as you know that because of convection, monsoon rainfall, they have very large impact on aerosol. If someday you see it was very rainy, so next day you see all aerosols are kind of washed out. So convection and monsoon dynamics, boundary layer dynamics, they have very big role in controlling aerosol distribution. So having accurate meteorological fields is very important for calculating aerosol distribution.
Okay, so thank you, Dr. Roja, for a wonderful talk by you. And we are all benefited by this informative discussion. And I'm really thankful to you for sparing out your valuable time and discuss the topic in our workshop today. Thank you so much.
Thank you, Manu. It has been an honor, and I am happy with the kind of questions people have asked. That is very good. So thank you and all the best.
So welcome back. We have the last speaker with us today, Mr. Akhilesh Kumar. He's currently pursuing PhD at University of New South Wales, Sydney, in the area of groundwater recharge process at Australia's National Groundwater Recharge Observing Sites using remote sensing and statistics. So he has done his master's under my supervision and he has developed a simplified iterative algorithm for aerosol optical depth estimation, which we had discussed in the session on remote sensing of aerosols through space. And it led to the development to a software which can be used for aerosol optical depth retrieval for multiple sensors. So, welcome, Akhilesh, to this one-day workshop. We will like to have from you a demonstration or hands-on training for aerosol and its aerosol products to our audience. Over to you, Akhilesh.
Thank you, ma'am, for amazing introduction. Uh, we will just go through it. If you want to tag along and access all the slides and the codes, some of the codes which are used here, you can scan this QR code and it will redirect you to GitHub repo where you can get all the codes. So, good evening, everyone, and welcome to the last session of the seminar. Now, this session will be in two parts. In first part, we'll be looking at how we can access and visualize some commonly available satellite AOD products as well as ground measurement based AOD data. And in the second part, we will have a demonstration of the IAOD software. So Manu ma'am previously had, like, she explained in quite a bit of detail about all this AOD data, so I'll not be dwelling much here. Uh, One of the most popular ones, however, is the Modis data, and they provide AOD products in both DB algorithm and using the DT algorithm. And this is what we'll be trying to learn how to download. We also have AOD data, but are not operational from satellites like Landsat and Sentinel-2. They are mostly created during the atmospheric correction process. In fact, we did a study, a global evaluation of the Sentinel-2 AOD data. The study I have linked at the bottom of this slide. In ground-based measurements, the most popular one is the AeroNet data. It's basically a network of ground-based sun photometers which are placed all across the globe. We'll also be seeing how we can access and process AeroNet data. So we'll first look at the Moody's deep blue and dark target data sets. Uh, Most of the Earth observation data from NASA, it's available at this servers called as DAC, and one of those DACs is the LADS, which holds the atmospheric data, and this is where we will go to access the Moody's data. Now, if you have access to the slides, you can see this on your screen and you can follow along. But I'll quickly switch to Chrome now, and we will try to look here. So this is how the deck looks like. And if you have an Earth Earth Engine login, you must do it because that's the way where you can access and finally download the data. So the first part is, of course, selecting the products. As you can see, there are lots of AOD data, but we're interested in the MODIS data. So we'll go to aerosol. We'll scroll down a bit, and you can see these products, which are MODIS AOD data from Terra and Aqua. Uh, 3K means that it is available at 3 kilometer resolution, and L2 means it is available at 10 kilometer. We'll just select one of them. Then in the next step, we have to select the time. Now we can get data for a single day, or we can give it a range of day. Uh, we will go with, say, 1 month of data here. And just so that you can match this with the slides, I'm selecting a data set for January 2023, the entire month of January. So once you have it, you just add it, and then you go to the next part, which is selecting the location or the area for which you want the data set. Now there are a few options here, countries, validation sets. So if you click on validation set, you see a lot of sites here, and this will give you point data for these sites. And one of them is the AeroNet, which is widely used for validation purposes. However, we will uh, draw a custom boundary box and try to get the data set for Indian subcontinent, some part of it. So once you have selected it, you just have to go to files. And now, depending on how big your selection is in terms of date as well as the area, it can take quite a bit of time. But once these results are loaded, it looks something like this. Let me go back. Okay, so this is how it looks after the results have been loaded. You just select whatever data sets you want. Originally, this data set is available in HDF format, which may not be easy for many people to work with who are not aware of it. But it also provides you various other options to reformat it in your preferred format. So if you go to the last option, which is the review and order. There you can, if you have multiple files, you can mosaic them into one single layer. You can reformat them into GeoTIFF, which is easiest to work with. You can also reproject it into different projection systems. And you can also select what kind of extra information you want with that. So it has information like the cloud fraction over land, cloud fraction over the water bodies, water vapor concentration. So you can choose to have those data sets as well. By default, the HDF file is not georeferenced. So before you order it, make sure that you select georeferencing. We'll go back to Chrome just to see if we have went somewhere. So it's still in the loading phase. Anyways, so once you have reviewed the order, you selected everything you want. Generally, after 10 to sometimes an hour, you get an email like this. It gives you a bunch of options through which you can access the data sets. If you're comfortable using the command terminal and want to automate things, then you can use just copy paste this thing in the terminal. But before you do that, you have to ensure that there's something called wget. It's a kind of an executable file which helps you access files over internet through terminal. So you have to get that downloaded and keep it in the working folder, which in Windows system is basically the C drive. And once you have it, you just copy paste it and it will start automatically downloading all the files that you have selected. Of course, you can also do this thing manually, and you can go to this link and download all the files one by one. Once you have it, and provided that you converted everything into a GeoTIFF layer, now it's easy to visualize. You can do it in any software that you have. It could be QGIS, ArcMap, or Envy, or whatever software you use. But you can also do this visualization programmatically. Uh, Now this code piece, it is available on the GitHub repo. This uses the raster.io package from Python, and it's a very simple set of lines, and you can visualize any data set which is a raster layer. If you're using R, then you can use a library called Terra, and it will do all the things that a raster file should can be done with. However, these data sets are available on the DAC server, so you have to do quite a bit of work. You have to select the files and get it. There are some data sets like this one, which this is also from Modis, by the way. And these data sets are available on Google Earth Engine. Now, the good thing about Google Earth Engine data is that you don't need to specifically download it before to use it. You can do the calculations, estimations, and every analysis on the server and then just download the final product. However, if you're inclined to download the data from Google Earth Engine, uh, and the native code for Google Earth Engine is JavaScript, but you can access those features through Python as well, through a library called Earth Engine API. And we'll try to see this uh, hands-on if hopefully it works. So what we need before we can access anything from Google Earth Engine is to have a project. And this project is unique to every user. It has to be created beforehand and it has to be registered. I have provided a link here where you can basically learn how to do it. So assuming that you already have or will have in future, uh, the way you access Google Earth Engine data is simply this. So what you need is an image collection, and an image collection is access something. So this is how the Google Earth Engine data looks. And this is the image collection. This is also unique to each data set. And we need this, and we go back, we provide this image collection, we give our preferred date range. And if we just want our data set for a small region, we can also provide a bounding box. Once you have it, you have to select a band. Now the band informations you can find on Google Earth Engine page. Just go here and you will see a list of names. So there is one which provides AOD data at 470 nanometers. There's one which provides data at 550 nanometers. We'll try to access the 550 nanometer data. So if you're using this Google Earth Engine for the very first time, you also need to authenticate and initialize. Now, both these processes are done automatically. So if you're using it for the first time, when you click on this, you will be asked to authorize, and we'll see briefly in a brief moment how it looks. Of course, it doesn't show me because I already have an authorized session, but in case you didn't have, it will open up a pop-up which will ask you to select your project and your uh, Google uh, Google account through which you are accessing that project. The steps are pretty simple. You just have to click on continue and it will get you there. So once you have it, you'll get something like this. It will give you a download link, which you can click on, and it will download you the data. Now, this data set, you can just open in any file, any software that you use. But the whole point of using Google Earth Engine is to avoid downloading the data. The point is to use the platform itself to visualize and analyze those data sets. So if you want to analyze raster data from Google Earth Engine, one of the very handy packages to use is the GMap. It has a lot of functionality, almost everything that you need to work with raster files. Uh, Everything is same. I'm still accessing the same data set. I'm accessing the same band. I'm giving it some visualization parameters, basically what kind of color palette I want for which range of data. And I'm just calling the gmap function. Now, if I click on it, I should get a map with my data loaded on it for my bounding box. So if I scroll down, this is how the data set looks like. This is the bounding box for which we selected the area. We can make it less transparent, more transparent, sorry. And you can see this is how the data set looks like. This is the MIAC data. And you can play around with it easily. It doesn't take much time to analyze and process and change dates and regions as well. Now, the other data set, satellite derived data set for AOD is from Sentinel-2. As I mentioned before, it is not an operational product. However, they do provide it. And if you want to use that data set, the procedure is same. The only thing which we need to change is the image collection. And for that, you go to the uh, Google Earth Engine page for this data set, and we grab the image collection library from here, and we just paste it there. And the band, since it's a level 2 product, it has all this surface reflectance data for all the bands. But if you scroll down, you see something called AOT, which is the aerosol optical depth. Here it's called thickness. This is the layer which provides AOD information. So this is about the satellite derived AOD products. Uh, I've written the codes in the slides as well. If you want to go through that route. Now the second data set that we'll try to learn how to access and process is the AirNet data, and this is a very important data set, particularly because it is most widely used, and in many cases, the only data set which you want to use for validating your retrieval using satellite data. And the way to access it is through the Aeronet site on NASA server. We'll go back again to the Chrome, and this is the website for Aeronet data. There are a few things which I want to highlight first. So this tells you about some of the versions of the data that is being provided to you. The most latest version is version 3. And in every version of the data, we also have different levels of accuracy of the data set. Uh, so we have level 1, which is the raw data. There has been no screening even for the cloudy pixels. Then we have level 1.5, which has been cloud screened and there has been some kind of quality control done on it. Level 1.5 is mostly a dataset which you would like to use because it is available almost in real time and it is fairly accurate for most purposes. But if you are concerned about more accuracy and are willing to wait for some time, you can also use level 2 product. In this demonstration, we will try to access level 1.5 dataset. So for that, we go to download tool here under the aerosol optical depth version 3 solar. And this is solar because it uses sun photometers, which Dr. Manu ma'am has talked about before in her presentation. So once you open that up, there are a few options which you can select. Let me go up. So these are the sites which are available, but keep in mind that not every site has information for every year. So a good practice is generally to check beforehand which year we want to access the data from. However, if you already have done it, then you can select a region. Let's select Asia. In the country, we'll select India. And these are the sites which are available for India. We'll go with one of the sites which has the longest record for Aeronet. It is the Kanpur site. So once you have it, we just click on that data set, and this will open up another box. And here we can select our time range, the level of data set that we want, all those things. Let me just select the same range which I have been doing for other products. We want aerosol optical depth with some extra information. So we'll select that. You can also select other informations if you want. And then once you have it, just download. It should open some pop-up box. And this basically gives you information about how that site is maintained, which researchers are responsible for that site, and whether there is some data set available for that. If there is in data set, then you'll get something like accept. You will have to do it, and then you can get a CSV file with lots of information. I've not downloaded it now, and I'll just jump to the presentation here. So once you go through all these steps, you can open this CSV file in Excel, and this is where the pre-processing starts. So if you're doing it manually, uh, then you will have to format it a bit. You'll have to get rid of some missing data points. And one of the important things which we do with this ground-based measurements are that we need to do some kind of temporal averaging. And by that, I mean that suppose your satellite over past time, or the time at which the satellite image was taken is 5 a.m. in the morning. Now you generally don't use AOD data for that exact time. What we rather do is we take an average of say 30 minutes before that time and 30 minutes after it, And this is done so that we can kind of average out the atmospheric disturbances that may be happening around that satellite over past time. And the way to do this in Excel is to, like filter the data sets, take the average and move on. But the problem with this approach is it's time consuming, it's very tedious, it gets boring if you have a lot of data points to work with. In fact, single point, single data, single day may take somewhere between 15 to 20 minutes to do processing. Now imagine if you have something like 50 dates to work with, and you'll be spending a week doing just the pre-processing for inner data. So what we did in AOD software, which I'll be demonstrating later, is give you a way to automatically do it in a matter of few minutes. So I will switch to IAOD software once, and we'll see how we can do this to the software. So this is how the interface looks like. We'll come back to it later, but for now, we are interested in something which is available under the main heading. There is something called AirNet extraction. It throws up an error that we need internet connection to work with, which can be set from here. Once you have set it to yes, and we click on it. Now, I mentioned before that not every site has data for every year. So you may want to look into that once. But let's suppose we want to get a data set for, say, 2023. And this is our satellite over past time. This information is generally present in the metadata file. So I will just give some random date here. So we are assuming that we want data for 2nd January at 5 in the morning. Now this is the temporal scale averaging. So I mentioned something like 30 minutes. You can also do 60 minutes or 15 minutes. Let's go with 16 minutes. And we want to download level 1.5 product. This is this wavelength is okay. So one thing that the AeroNet data has is it has AOD information at multiple wavelengths, but your satellite data may not be available at that wavelength. So you may want to uh, get AOD at your own wavelength. And you can do that here. It uses something called angstrom equation in the backend. Again, if you have attended Manu Man's lecture, you would know what that is. So suppose we want to get it at 550 nanometers, for instance. We just put that here. Now we will need a raster file, and this is just to give it an extent. Uh, so basically a bounding box where it can search for the AeroNet sites. We will see if, so I'm giving it a Landsat data that I have with me. And we also need to provide it with a destination. And this folder will have all the files that are being downloaded from AeroNet, including the list of AeroNet sites, uh, the raw files, as well as the pre-processed, as well as the processed files. So I want to save this in this folder called Landsat 8. And now if you click on extract AeroNet AOD, it will try to connect to the internet for the year 2023. It will search up all the sites, and it says that it has found 2 AeroNet sites for year 2023 on this date. But then we also see these 2 messages, which shows that there were no data available for those dates. So let's try something which we already know, which I already know that there is a data set for. So we'll go back to this and we'll try again. And this time we have at least data for one site. Now, if you want to view the results here, you can do so, and it will show you how the dataset looks like. But if you want to also get the AOD at your own preferred wavelength, you just need to provide a wavelength here in nanometers and then click on calculate angstrom AOD. It will do the calculations for you and we'll get a nice table with this information. So we have data on this date for Amity University. This is one of the AirNet sites in 2021, and AOD at 550 is 1.32. So what this software does is that it massively reduces your, you know, the time that you would need to process the AirNet data, and you can quickly use it for any kind of validation. Uh, when we are having the AOD demonstration, I will show you how it can be used programmatically within the IOD software. So yeah, basically this is the summary of how you can do it there. Now we will go to the second part of this seminar, the session, and this is the live demonstration of the IAOD software. So Manu ma'am has had mentioned in brief that it's a physics-based iterative approach for AOD retrieval from different sensors, and the basic flowchart looks like this. Now I will not go through it. Of course, she had already went through. But what I want to highlight is there are a few parts in this algorithm which is automatically done by the software itself, and we don't need to do anything. And this includes uh, doing the atmospheric corrections and iterating through multiple asymmetry and SSA values, and then giving you an AOD value in the end. However, since the approach is iterative, there are also some user interventions needed, and this uh, interventions are really required when we are trying to provide the parameters, uh, the asymmetry parameter and the SSA parameter, as well as a reference AOD value, at least one value every scene. Now, this iterative approach looks something like this. Now, this is just a way to kind of reduce the computation while still getting a very precise value of AOD up to 3 decimal places. And there's a paper here which kind of explains this methodology in great details, along with all the necessary parameterizations. But what we are concerned about is just 3 steps. And one is we use percentile values to segment the Rayleigh collected reflectance image. What that thing is, you will get it once you read the paper. That would be easier. Uh, and this percentile ranges we have to provide. Of course, there is a default value already built in, but you can change it. Once you have these segments, you want to assign asymmetry values to them. And this is a purely user-based intervention. The default values don't work so well. And the third thing that you would want to intervene with is providing a single scattering albedo values. And once you have it, it should just work like a charm. So we'll stop it here and we'll go back to our software. I will close this Aeronet thing. So this is how the software looks like, the front end. And if you need information or like how to access different components, different modules of this software, what kind of data sets to use, you can go to About section and there's a help document. Uh, it's very thorough and you can look through every component of it, including the formatting of data sets, which kind of sensors you can work with, what is asymmetry, how do you do it, things like that. Now there are there's 5 sensors for which we have developed this software. However, it can be used for most sensors as long as we have as long as we satisfy the initial data format requirements. So let's select Landsat 8, 9, because they have the same number of bands. Then we can select a band. If you're not sure of which band is available for which sensor, you can also click on check availability and it will check for you. Now we have to select an operation. We want to retrieve AOD. And if you go on save and next, it opens something up. It will want you to include all these files, basically the radiance file and the angle files. Optionally, you can also provide a cloud mask layer, which is provided by Landsat. Uh, but there's a word of caution. Sometimes the cloud mask layer, it also removes the important and information worthy pixels. So be prepared for that. However, you can choose not to apply cloud mask by deselecting everything and save and close. Now this is for Landsat 8, but not every sensor provides the dataset in same format. For instance, if you have Sentinel-2 data, it does not provide you with angle files. However, it has an XML file which has some information about angle, and we can use that information to recreate the angle files. For instance, if I click on Sentinel-2, let's check if B1 is available. And now if I go to save and next, it will ask for a prompt like whether you want to generate angle files or do you already have it. If you have it, you can select no, or if you have don't have it, you can generate it and it will require the XML file and it will do the thing for you. But let's go and just look for Landsat 8 for the moment. We don't want to apply any cloud layer. And we just have to browse. Now you can do this browsing thing in two ways. You can manually provide each of the layers one by one, or you can use something called a control file, which basically is a shortcut for providing all these data sets. How that thing looks, it's provided in the help document, and you can create it and use it. However, what I will do is I will use this, I will provide all these files manually so that you can see which files are being used. So this is for the solar azimuth angle, which is the SZA layer here. Then we need to provide the zenith. I think I messed it up. Let me go again. So I had mistakenly put a zenith angle in azimuth, so I'm redoing it. It's probably a good idea to use the control files because then you don't have to do it one by one. It's much faster. And if you had selected a cloud mask layer, you also need to provide a cloud mask layer here. But I don't want to use it, and so I will leave this thing blank. And now we want to provide the metadata file from which it can get all other informations like satellite overpass time, for instance, or what kind of correction factors are being used for different bands. Once you have it, we just go to save and next, manual. uh, since we are short on time, we will also resample the dataset to a coarser resolution. Let's choose 1,000 meters for now. Of course, you will want to do it at a much smaller resolution or a subset of the dataset. But for this purposes, let's say we are resampling it. Once we have done it, in the backend, it has done all the calculations for you. Basically, it has converted the raw radiance files into reflectance images. It has done these atmospheric corrections, and there is a surface reflectance file in the backend somewhere. And now this is the first step where you need active manual intervention. And this is where you want to provide a single scattering albedo values. For that, uh, The ranges differ, but anything from 0.8 to 1 works fairly well for Indian subcontinent, especially the northern part. So let's say we use 0.85. Now I'm putting these values arbitrarily, but it's always a good idea to look into literature and see, or just try different values until you see what works best. You can also apply a convolution layer so you can smoothen the AOD product. This is useful, especially in cases where you may have some spurious pixels with unusually high reflectance values. So you may want to paper that over so you can do convolution. Once you have provided the SSA data, and a new window opens up, and this is perhaps the one which requires most intervention from you, and it also has a lot of information to work with. So basically what we want to do, as I mentioned before, you first need to provide percentile values so that you can segment the Rayleigh corrected TO reflectance into into certain parts, and that is done on the basis of how bright the pixels are. So these are the pixel percentile values. So we want to segment it based on 5 percentile, 40 percentile, 60, 80, and I've added another one, say 90 percentile as well. Uh, and the second step is to input the asymmetry values. But before we want to do that, there's something else we need to also work on. Now, if you see here, the web connectivity is already turned on. We turned it before. So what it does is, if there's an internet connection, it will go to the aeronaut website. It will do all the fetching for you, and basically it shows you which percentile segments have what range for their TOA values, and what each aeronet site uh, which erroneous site falls on which percentile segment. And the reason it is important is because this information we can use to provide a reference AOD value through which the software will try to estimate AOD for other pixels. It also gives you surface reflectance and Rayleigh corrected reflectance values, which we don't basically need it. Maybe we need your reflectance for now. And what we want to do is go to AirNet AOD because we want a reference AOD data. And it's basically the same step that we did before. I won't change anything here, but I will provide it with a reference raster data so that it can get the extent. Let's provide the destination folder, and it will do the same thing. It will go to AeroNet, it will fetch the data set, and since we selected band 1, and band 1 is at 413 nanometer for Lancet, so we want AOD at 413 nanometers. That's why I have put this value here. We click on angstrom AOD, and we get this thing. So back here in this console, you see these values here, that for IIT Delhi, we have this AOD value. We also have a RCR, which is the Rayleigh corrected reflectance value. We have a surface reflectance value and a percentile range along with TOA value. Now, this information is useful for us. I'll close it for a bit because what we can do is there's something called check here for asymmetry assistance. And if you click on this, you get a nice table here. So coastal aerosol is the band 1 for Lancet. There's a similar name for Sentinel-2 as well. Indian sensors like LEAS-3 and AWIFs generally don't have coastal aerosols or blue band for that matter. So green, red, and NI are available for Indian sensor. If you select band 1, which is the coastal aerosol, it shows you something, basically AOD values, TOA, and what kind of symmetry it has. This is the tabular form, but you can have an interactive plot. And if you go back once, the AOD is around 0.93. The TOA value is about around 0.10, and that is for Delhi. If you come back here and hover around a bit, so let's say somewhere here maybe, this is 0.93, and you want to go to TOA value of 0.10. So you see that the asymmetry for that region has to be around 0.5 or maybe 0.56. And we know that this AirNet reference AirNet site, it falls on percentile range 40 to 60. So we go back to this asymmetry segmentation. Of course, you can use a single asymmetry value for the entire scene. Uh, this is useful if you don't know much about asymmetry or if it's a very small scene. But for larger swath satellite data, you may want to provide different asymmetry values for each percentile range. One thing that has to be kept in mind is that the asymmetry value that you provide here does not represent the actual optical properties. Uh, it's approximation which we need for driving this physics-based interactive algorithm. So if we click on advanced option, there's a way to provide asymmetry for all the percentile range. So 40 to 60 was our reference AOD data, and we saw that we need to provide something around 0.58 as asymmetry for it. And then here you can see that for the other percentile range, you can use an asymmetry which is 3 to 4% plus minus the reference value. So I'll arbitrarily just put something like, say, 0.56 for the percentile above, 0.58 for the first percentile. Sorry, is the reflectance values and asymmetry generally have inverse relation. So for lower percentile, you would want to have a higher asymmetry value. So let's just say 0.60. I can put 0.62 here. And similarly, 3 to 4% lower, we can put down 0.56, for instance, 0.54, maybe 0.52 here. Once you have it, we just click Save and Next, and the retrieval process starts. Now, depending on how big a scene, a satellite scene you have, it can take anywhere between 10 minutes to even an hour. But we had resampled this Landsat data at 1000, so it's a pretty small coarse resolution data set now. And it should take around 2 to 3 minutes for retrieval process to continue, to complete rather. And we'll wait for it. And once you have this retrieval done, you can, the output will be available as GeoTIFF layers, and you can visualize it again either programmatically in Python or R, or you can do so in any software like QGIS or ArcMap. There's one thing which I want to show you, and that's why I'm waiting here. While that happens, we will come back here. And the presentation, it has a small video which shows all these steps for you. So if you want to catch up on it later, you can just reference this video and you can do it for yourself. We are waiting for the AOD retrieval to happen in the backend. Let's check what's happening there. So this is the console which shows all the inputs that you have given. You can save it for future references. It has the file names as well as the information about your asymmetry range, the percentile values that were being used, the TOA values, everything for each of the segments. And it's at 90% at the moment. Should be done pretty soon. Okay, the retrieval is done. And since we were still connected to the internet, so what it does is it also extracts you and gives you the AOD values for uh, both the AeroNet site. As you would remember, we had no information for MET, but now we do have a AOD value for that. And this one says that the retrieved AOD is 0.69 for IIT Delhi, but the value was supposed to be around 0.93, which means that in the next iteration, you need to change the asymmetry or the SSA values, or maybe both, and keep on iterating it until you get the good value for the reference AirNet data. Once you have it, the entire data set is like the retrieved AOD is available for you. And then you can go back to your folder and it will have all the data sets. So we have the AOD data set, and if you have a QGIS, which then you can have a look at it. And this is basically the presentation that I had to give it to you. We'll just have a brief look at how our AOD layer looks. Of course, we need to iterate it again since we are still behind the reference AOD value. Taking a bit of time, I guess. In the meantime, I request Manu ma'am to please start the procedure for a questioning and answer session so that we can wrap it up quickly then.
Students, I think, yeah, parallelly you can take them one by one. So, one question is, what are the challenges of comparing aerosol optical depth from AeroNet and satellite data sets?
So one of the challenges is that you have to pre-process it. You have to access the data set. Now for satellite images, it's fairly easy. You have servers where you can do that. You can get the data set. But for AeroNet, you'll have to do a bit of manual intervention if you're doing it manually. The second thing is you also need to be aware of the metadata of this data sets, like the spatial resolution at which it is available, uh, and what kind of AOD value it has, whether it is at 550 nanometers, whether it is a corrected AOD data, things like that. But the biggest is that you need to know where to get this data set from. So for I've shown it for MODIS, but every AOD data has its own platform where you can get the data from. So these are like
Correct.
three major challenges that you face.
Yeah. And then which programming language, Python, MATLAB, or R, are most useful for aerosol data processing, and what level of proficiency is expected for effective hands-on?
So I don't know much about MATLAB. I'm not at all proficient in it, so I can't answer that. Uh, but there is a Terra package in R, which is very easy to use. However, R has some issues with spatial data. It takes a bit of time. So that depends on you. If you're comfortable with R, you can use it. However, I have personally found that Python is much easier to work with. You have something like a GDAL package, which is pretty basic. You also have something like raster IO or Rio X arrays, and those are pretty easy to use. So Python will be my preference.
Yeah.
Yeah.
And connected to that, which open source tool or software are most effective for hands-on aerosol data processing?
Well, we saw Excel is pretty good at it, doing the for the AeroNet data at least. And for other satellite data, I think something like QGIS is good enough. However, you will have to do some pre-processing, basically converting those files into your preferred file format, like from HDF file or NetCDF file to say GeoTIFF, which is easier to work.
Okay, so one last question we can take. What are the common data issues encountered while working with real aerosol data sets, and how can you handle them?
Okay, so the real is if you are using MODIS data, for instance, there are certain regions where you will not get the data. There's no retrieval, basically the bright surface areas. So those are our blind spots. Uh, in certain regions, there have been studies done. For example, we see that MODIS data at 10-kilometer resolution, it performs slightly better over like heavily polluted areas, but 3-kilometer resolution data doesn't. So these are some operational issues with these data sets. Uh, I think that's it. I mean, there's nothing
Yeah,
else. Yeah.
yeah. Cloud contamination can also be there. Then some missing data in the form of nans and negatives you can encounter. You can screen them all. You can write a small function to screen that. Yes,
Yeah.
so the visualization is ready, Akhilesh. I think with that we can wind up.
Yes, you can see it here. It's just there. Values are ranging from minus 0.1, which it should not, and it does not. It's mostly the edges where you're getting zero minus values, and this is how it looks. And you can iterate it again and get a even better AOD values. Yeah.
Yeah, thank you, Akhilesh. Thank you so much for such a clear, illustrative, hands-on training for the participants, spanning from downloading and visualizing the operational data products and satellite products as well as Aeronet products, and then coming to the software that you developed. So thank you so much for a wonderful session by you. Thank you. Thank you so
Thank
much.
you very much, ma'am. It was a pleasure. Thank you.
Yeah. So that's all from IIRS today, and this was the one-day workshop focused on providing an overview of aerosol measurement impacts and its fundamentals, along with the retrieval algorithms. Now, this should be just a beginning for inculcating your interest in aerosol research and taking it up further into developing some new, addressing some new challenges in the aerosol research. Thank you so much. Namaskar.